You will cover intuitionistic logic, yeah?
Yes.
Okay, I think I have to stop talking now because this computer has to be switched off.
Oh, I see. Okay.
Or, I mean, not switched off, muted, so that there is no echo in the room. There is another master computer there. So I will stop talking.
I think there are some people in the waiting room. Is that, shall I let them in?
No, we'll let them in once the Purvita just arrived, so we'll let them in. You don't need to worry about those people. We'll transfer the messages to you as well.
Okay.
Oh, hi, Nick.
Hello.
This is Purvita actually. Yeah. Oh, the video is.
Oh, hi, Purvita. I can't see you. Yeah. Okay. Now I see.
Yeah. We have already checked that your slide is working and all. Good.
Yes. Let's see. Yeah, I think so. Yeah. Yeah,
what
you see.
Time
right?
now at like I forget time difference now.
What's that, sorry? Time difference. Well, in Amsterdam it's 10:30 now, so it's not so bad. The first lecture is at 6, right? So that's
yeah, it's too early.
Possible to make. Yeah, then 8 is also difficult, and also today I had to attend my students' talk in Australia at 8. So. Yeah, that's one thing, right? When you are when you're attending an online conference, right? So it's not that you are saying goodbye to your duties, right? So you're attending online, but you also have all your duties where you are, right? Yeah. So here I still have lectures, I still have committee meetings and all that.
Oh yeah.
In old days I could have said, I'm going to Isla, bye-bye. So you do everything without me. But now you are kind of split on many different fronts.
Yeah. So how many participants are there? 9 only now.
We should wait for 3 more minutes.
Yeah, sure. Oh, yeah. Also, like our offline participants are already not arrived, all of them, right? I can't see all.
Jaskirat is missing, that's
yeah.
Bidhan,
no, Prashanjit and Bidhan.
Prasenjit was not there today at all.
But maybe this lecture he's supposed to come, I'm not sure. So I think the why we off these lights, these lights. Oh, it makes the difference. Okay, that's good.
Hi, Nick.
Nick, actually, oh yeah, Marcus is here. Hi, Marcus. Actually, yeah, Nick, I guess that one tutor will be enough for your tutorial, because we are not like in online, naturally we are getting not more than 35 pupils at least. Like And in online mode, we have approximately 13 or to 15 people. So
yeah,
it's up to you, because we actually break rooms for our tutorial. But today, for the category theory, it was just one. So it's up to you, whatever you can.
I already told two. I mean, two of them could be in one room as well.
Yeah, that can be done. Yeah. So we will start dot at 2 or not really? It's 12 now. Yeah, that's bad. We can start and let they join. I think that will be better. Okay, so welcome to the second part of the third day. And today our speaker is Professor Nick Bezhanishvili from Institute for Logic, Language and Computation of University of Amsterdam. And he is going to present the work on Tressl type dualities, and 2 consecutive talks will be there, followed by a tutorial tomorrow. Yeah, that's it. I hope that you will get some of the ideas from here as well. And the platform is all yours, Nick. Please take the charge.
Thank you very much, Purvita. I just lost my...
the share screen, you mean?
Yes. I see. I think I know what happened. Okay, just 1 second. Yeah, I think now I got. Do you see it?
Yeah.
Okay, now I should put full screen. Yes, now you see it. Yeah?
Perfect. Yeah.
Okay, yeah, sorry about that. Okay, well, thanks very much, Purvita, for this introduction, and thank you and Amit and other organizers for inviting me to give this lecture. Yeah, in fact, I find the school very nice, very focused. I mean, one of the most focused schools I've seen. Really, a lot of different lectures centering around the same topic. And I also want to apologize to some of the lecturers. I would love to attend all the talks, but there's time difference, and plus, as I was telling to some of you, well, with online conferences, it's a bit difficult. You still have your duties, so I still have lectures in Amsterdam, committee meetings in Amsterdam, and also it's a bit hard to, and also the school lectures, right? So it's a bit hard to manage all that. But I enjoyed all the lectures that I've attended so far. Okay, so what I'm going to talk about, this will be really, as I said, continuation of some of the talks that were given, lectures that were given at the school, for example. In particular, this will be a continuation of the lecture given by Mohan Banerjee on stone duality. And in fact, this tutorial, this lecture will be also closely related to Marcus Tressl's tutorial on spectral spaces. There will be a lot of close connections there. Now, before that, let me quickly say a few words about my research. It's centered around the theme of the school. I work on algebraic and topological methods in logic. And in fact, I often call my area of research TACL. TACL stands for Topology, Algebra, and Categories in Logic. And in fact, TACL is also a conference on this topic. And in fact, TACL 22, this 2022 installment, is going to take place this year in June in Portugal. Okay, so again, to summarize, how is topology, algebra, and categories related? I call it a triangle. So we have logic here, as one edge of the triangle is logic, Another one is algebra, and here you could put topology, spaces, or order and topology. And connection between logic and algebra is given by algebraic semantics. Well, here we have relational semantics or topological semantics between logic and topology. And here we have a duality, and this is what we want to concentrate on here. Duality between algebra and topology. So two different worlds connected by categorical dualities. And this is exactly, you've seen already, if here we put Boolean algebras, then here we'll get stone spaces. Today we'll see that if on the algebra side we'll put distributive lattices, then on this side we'll get ordered topological structures, Tressl spaces, and in Marcus's talk you will see that this is the same to put here spectral spaces. Time permitting, tomorrow I'll try to also discuss some more connection. Well, we'll concentrate on this part, but time permitting, tomorrow I'll also at least say a few words about how logic is connected to that. But you already seen this in many of the lectures at the school. Okay, so examples of these connections, and this you've seen at the school: classical logic. This is on logic side, Boolean algebra on the algebra side, stone spaces on the spatial side, topology side. Today we'll see this connection. So distributive lattices on one side and Tressl spaces on the other, and here we have positive logic. This is the logical counterpart. Tomorrow we'll talk a bit about intuitionistic logic and the connection, and a lot about connection between hating algebras and Esaki spaces. This we will not talk about here at this school, but something also to know that we have model logic on logical side, model algebras, Boolean algebras with operators, and corresponding spatial structures or the topological spaces. But well, for the lack of time, we will not cover this, and this list goes on. Now again, let me quickly remind you. The literature. I'll be using Davy and Tressl, Lattice Order, excellent book, and also Esakia's recently published book, but this is a recent English translation of a 1985 monograph, which was originally published in Russian. So this also, so roughly speaking, for Tressl spaces, for Tressl dual, for first lecture, we'll be using this reference, and for the second one, this. I also teach a course at the University of Amsterdam called Mathematical Structures in Logic, which is centered around the same topics, and I'm also will be following that. Unfortunately, I have lecture notes, but they are not in a shape to be circulated, so I'm afraid. But I'm using those. Well, at least the material from the notes I'm using here, I'll be using here. Okay, now let me. This is what I want to assume. So lattices and order, because there was a tutorial of that at this school. So I don't think I need to define what a distributive lattice is and what a Boolean algebra is. Filters and prime filters, this you should have also seen. Topological spaces, in particular stone spaces, you had also tutorial on that. And I assume, although I'll quickly remind you, but I assume stone representation for Boolean algebras and representation of finite Boolean algebra. These were all covered so far. Oh, and for the next lecture, one quick question. Can I assume that you've seen hating algebras, or that I need to define?
So people don't know the hating algebra, many. So better to define.
Better define, okay. Okay, well, but that's for tomorrow. Okay, now, let's start with stone duality, and then, this area, you could say, has started with this celebrated fundamental work of Marshall Stone. So a stone space, as seen, is a totally separated or totally disconnected compact space. So where totally separated means that every 2 points are separated by Kloppen set. An alternative definition is that a stone space is a compact Hausdorff and with a basis of Kloppens. It's a good exercise to see that these two definitions are the same. And the representation that was already proved at the previous in the previous lectures is that every Boolean algebra A is isomorphic to Boolean algebra of Kloppens of some stone space. And in fact, this is a particular case of a more general categorical duality, that the category stating that the category of Boolean algebras and Boolean algebra homomorphisms is dual to the category of stone spaces and continuous maps. So you've seen this too. In short, BA is dually. So OP duality stands here for OP. And why is it duality? Because there's not a covariant functor, but these functors are contravariant. So they reverse the errors. Now, the most beautiful thing in my view about this duality is that, well, it connects two different worlds, algebraic worlds and topological worlds. And this is and we can translate concepts from algebra to topology and backwards. This I call a duality dictionary. So again, I'm not going to go through this, but you see that here we have concepts on the algebra side, homomorphism, filter, ideal, maximal filter, and so on, subalgebra product. And on the other hand, we have is analogous with dual notions on the topological side. For example, filter corresponds to a closed set, and so on. So that's well, it requires some work to obtain this correspondence. But basically, this tells us that I can do everything. Well, I can translate algebraic concepts into spatial ones. And why is this good? Because if we want to solve some problem, well, from triangle, it goes like that. So we have a problem about logic. First, we translate it in algebraic terms. Then, but it still might be difficult to solve. So then from algebra using duality, this problem, which is formulated now in algebraic terms, we translate into topological terms, and then use kind of this geometric or spatial intuition to solve this problem. So this is kind of this game of the triangle. Let me give you one very simple example of that. So suppose we have a question. Is there a Boolean algebra with no atoms? Okay, well, the answer is positive, but and you could do it without any topology. But now we could use our duality dictionary. We can do some kind of a Google Translate, if you like, right? Duality translate. And well, we look at, I claim that this translates, well, Boolean algebra dually is a stone space. Well, if you look at the duality dictionary, atom means an isolated point which is a Kloppen. So we get that this sentence, is a Boolean algebra with no atoms, is translated to is a stone space with no isolated points. Well, this is easier to solve, at least, well, if we from topological perspective, because it's well-known fact in topology that this so-called Cantor space, which if you've seen, very good, if not, that doesn't matter, is a stone space with no isolated points. So we solved our problem. Now we take the Kloppens of the Cantor space, so going back to algebra, is a Boolean algebra with no isolated points. So just in one step, we just solved our problem using, again, topological knowledge or topological intuition. Okay, so this is just one simple example, and there are, of course, many more. In fact, I personally always think, so if you ask me some question about algebra, even if it could be solved on the algebra side, I always translate it into terms of stone spaces and then try to solve it there. Now, if time permitting, maybe I'll try to give some more examples of that. But what I want to talk about is the main topic of today's lecture is a Priestley duality for distributive lattices. Now, let's recall the classic example of a distributive lattice, and this I believe you should have seen in the first tutorial. So if X is a poset, so with set with a relation which is reflexive, transitive, and anti-symmetric, and an upset is a set which is upward closed, right? So if X is in U and X is Y, Y is also in U. I presume you've seen this in Sujata's tutorial. And then up X will be it's just a collection of all upsets of a poset. And then it is easy to see that the set of upsets it forms a distributive lattice. It forms a lattice which is distributive, right? So where the meets and joins are union in intersection, and then they bounce. Yeah, in this tutorial, every distributive lattice that we are going to consider are bounded. So they have the top and bottom elements. So usually such lattices are called bounded, but let's assume that every lattice that we're going to consider today is bounded. So when I mention distributive lattices, I assume bounded. In fact, we'll see that every finite distributive lattice is of this form, but not every lattice is isomorphic. Every distributive lattice is isomorphic to up of x. In fact, if you want to see an analogy, up of x plays the same role to some extent for distributive lattices that the power set of x of a set plays for Boolean algebras. If you remember, every finite Boolean algebra is isomorphic to the power set of some finite set. The same situation is here, and also not every Boolean algebra is isomorphic to the power set, and then we have the same here. Now let's see why not, and also just because I don't see your faces, I just don't. I cannot even tell with your facial expressions whether you are following or not. So maybe let me just ask this question. Not every distributive lattice is isomorphic to up x. So question to the students, why is that the case? Maybe it's a bit, it's not absolutely trivial. I don't know whether you've seen it in the Boolean case. Why not every
any idea from the offline participants?
Okay, maybe let me give you a hint, right? So I claim that up of x is a complete lattice. Complete lattice means that any suprema and infima exists for any subset. And in particular, I claim that this is an easy exercise to check, that the infima is just the intersection and suprema is the union. Well, then now I say that, well, this is always a complete lattice, but they exist non-complete, incomplete distributive lattices. For example, take 0-1 interval or any chain which is not complete, right? Say 0-1 interval, and let's remove the point half. Or you could take rationals, irrationals, whatever. Take your favorite incomplete linear chain, say, with top and bottom elements. That would be an example of a distributive lattice which is not complete. So it cannot be, not every distributive lattice is isomorphic to that. Okay. Nevertheless, like in the case of Boolean algebras, every distributive lattice can be embedded into up of x. So it's not isomorphic, but it's a subalgebra or isomorphic to a subalgebra of up of x for some x. Let's sketch this. The construction is very similar to Stone duality for Boolean algebras. We take a distributive lattice A and let XA be, as in the Stone case, the set of all prime filters of A. Again, I assume that you are familiar with the definition of prime filter, right? It was already discussed in the other tutorial, in the other lecture, right? So this is those filters such that if A or B is in the filter, then either A is there or B is there. And we order this by inclusion, this set. Okay, so this prime filters ordered by inclusion becomes a poset. Well, this is clearly a poset. Define a Stone map, which is you've also seen in the Stone duality tutorial. Stone map is that every element, so phi from A to the power set, is maps every element to the set of all prime elements here, all prime filters that contain A. Now, I claim that this is a bounded lattice embedding. Again, the proof is very similar, or maybe the same, if you like, to the Boolean case. Let's very quickly sketch it. Well, at least one thing we need to show is that phi of A is an upset. Maybe again, just to make sure that you are with me, does anyone see why would that phi of A, why is this an upset? Again, to
Okay. Yeah.
remind you, this is the definition of phi of A.
Yeah.
Sir, because any B which is a superset of A, and if A is in phi of A, then B would be in A. So, so A is less than B and B is in A.
Yes, very good indeed. So this is so. Suppose X, let X be in phi of A and X be smaller than Y. So X upset. So these are prime filters. Then X is in phi of A means this is equivalent to saying that A is in X. So A is in X, X is a subset of Y, so A is in Y. And that is equivalent to saying that Y is in phi of A. So indeed, from X being in the set, X being smaller than Y, we get that Y is in. So phi of A is an upset. Okay, very good. So at least it's well defined. Now, I claim that it's in fact a homomorphism. So it's yeah. So it's well, it's not an embedding yet. So it is yeah, well-defined homomorphism. Why is that lattice morphism? So let's see, phi of phi of 1. This is, we'll look at all the prime filters that contain 1. Why this should be X of A. So this is all the X everywhere here should be X of A. Sorry about that. So this is one of this algebra. So this is X. 0 is again all the prime filters that contain 0. No prime filter contains 0. So this is empty set. Maybe let's do this one. So if phi of A, this is the set of those filters that contain A or B. But from the fact that A is prime, F is prime, it follows that A is in F or B is in F. So it gives me this inclusion. And the other way around, if A is in F and B is in F, because A or B is greater than A or greater than B, then we have the other inclusion as well. So this set is equal to this set. And then, well, this set is the same as this or that, this union, right? And then we get that this is phi A or phi B, which is the join in this lattice. Okay, is this clear? Are there any questions? This is easy, but quite important.
Yeah. Yes, from the offline participants.
Sorry, Purbita, I didn't hear. Is there?
Yeah, I told that it's yes from the offline participants.
Okay, great. Okay, yeah, I see that now I was a bit too quick here. So I say that stone map is a bounded lattice embedding. In fact, I haven't shown injectivity yet, and I apologize. Let's assume that it's injective. We'll see. I have it separately. I should have moved it here. So suppose we also showed that it's an embedding, but this will require something. Then we are done. Then we have phi, which would be an embedding from A to apex A, but we'll get to that. Now the question is, okay, this is embedded in here, but or maybe maybe to be honest, maybe let's show that it's an embedding. So and then I'll come back to. Yeah. For injective, so we want to show that it's an embedding. It's done in the exact same way as it is done for Boolean algebras. Suppose A is different from B, right? We want to show that phi of A is different from that. Now, without loss of generality, we assume that A is not smaller than B, right? So if I were to draw it, that would be here. Say this is my algebra, say. Here we have A, and here we have B. So A is not equal because it's anti-symmetric. Then we have, without loss of generality, that A is not smaller than B. So everything above A is not below B. So A intersected B. A has empty intersection with up arrow A has empty intersection with down arrow B. Now, it's well known that up arrow of A is a filter and down arrow of B is an ideal. And the prime filter theorem that you probably have seen already in Boolean cases, and it's exact same result for distributive lattices. The prime filter theorem tells us that then there exists a prime filter, some prime filter here, F, that contains A and still has an empty intersection with B, with down arrow B. But that means that B is not in F and A is in F, right? Because A is there, B is not there. But this exactly means that F prime filter is in phi of A and F is not in phi of B. And so we get that phi is indeed injective. And so now it's fair to say that phi is an embedding. Is that clear? Note that we are essentially using the fact that that we have prime filter theorem. Okay, I want to remove this. Okay. Okay, now let's go back to what I. Yes, we do have an embedding, but what we want is more. We want to characterize this phi image. We want to have kind of an isomorphism. Embedding is good, but isomorphism is better. I want to have an analog of the Stone theorem that how should I think of every distributive lattice? Like what kind of upsets would I get? And for that, like in the Stone case, we need to define topology on X of A. And with this topology, we'll get exactly characterize those upsets that correspond to elements of A. So this phi image will be, and again, it's a bit similar. So then that will be Kloppen upsets in the inappropriate topology. How do we generate the topology? Okay, the first attempt is exactly as in the case of Stone spaces. We take topology generated by the basis phi of A. This is what we did in the Stone case. And we can do it then, and this is the direction that Stone took, right? So after proving representation for Boolean algebras, he proved the representation of distributive lattices. So to avoid some terminology, I'm again formulating it in terms of an embedding. So every distributive lattice is embedded into distributive lattice of open sets of some topological space. In fact, this space, XA with this topology. What space we will get? We will get a spectral space. And I, at this point, delegate you and encourage you strongly to attend Marcus's lecture, because he will be exactly talking about spectral space. So this is one direction. We can take phi of A's and we end up with spectral space. Now, I personally love spectral spaces, but you know, if one wants to be critical, they are nice, but it's a bit of a, well, I mean, you'll see even the formulation takes a few items. And they do not have all the nice properties of Stone spaces. In particular, spectral spaces are not Hausdorff. Stone spaces, on the other hand, are Hausdorff, extremely totally separated and so on, totally disconnected. So this is a nice class of spaces. So we want to work with Stone spaces, and spectral spaces are not like that. So what to do? Well, one way is to work with spectral spaces, accept the reality and still notice that it's a great class of spaces, or different one, and this is the approach that Tressl took, to, well, let's extend the topology. So we had phi of A's, right? But now we also take the complements of phi of A's, but and generate topology with this, or in topological terminology, take a topology generated by this sub-basis. Alternatively, if you would like to think in terms of basis, you just take phi A minus phi B and declare this as a basis. So basically, what does a sub-basis mean? I don't know, Purvita, you probably covered it, but basically think of this. You take finite intersections of this set and then unions of what you get. And this is the open sets are unions of finite intersections. Okay, and this is also called the patch topology, and I suppose Marcus will talk about this. So this is basically what we are taking is the patch topology of the Stone topology of omega A. Okay, now what we'll get now, the question is, what kind of space do we get? So we took distributive lattice, we took prime filters, we took the stone topology and its patch topology, and we also took the order, the inclusion. And the question is, what did we get? And now the point is that I claim that we get a Priestley space, and with this topology, A is isomorphic to Kloppen upsets. So now my next goal is to define what a Priestley space is, and finally to show this kind of representation, Priestley representation. Again, you see kind of similarity with the stone representation. Again, we're talking about Kloppen sets, but now we're talking about upsets. Now, if this Priestley space turns out to be a stone, well, we'll see it's a stone space. So if this less than or equal is equality, then upsets will be just any subset. And so basically then we get stone representation, because then we get Kloppens of XA. Okay, so this was this representation was developed by Hilary Priestley in the 70s. In fact, if I remember correctly, this should have been her first or one of the first papers she ever published, maybe second or third paper. So it was done in the 70s, in 70 and 72. In 2 papers. Okay, so what's a Priestley space? It's a topological space with an order, so order topological space, such that X is a compact space, and this is a partial order satisfying the following separation axiom. So again, if I were to draw, so if X is not small, so if Y is not below X, right? So Y is somewhere here, then there exists a Kloppen upset containing X and not containing. So this is my Kloppen upset U, which contains X, does not contain Y. So this kind of a separation. Okay. Now, question to you. I basically said it, but every Priestley space is a stone space. So if I forget about about the order, this is a stone space. Why is that? So stone spaces are compact and totally separated. So every distinct points are separated by Kloppen sets. Why is Priestley underlying space or Priestley space a stone space? Maybe question to the audience, so to make sure that.
Sir, because every X for every X or Y, either X will not be less than equal to Y, or Y will not be less than equal to X, and then there exists a stone space. There exists a Kloppen set such that X will be in that set, and Y will not be in that set.
So if X is not equal, yeah, exactly right. So if X not equal to Y, without loss of generality, so either X is not smaller than Y or Y is not smaller than X, because otherwise they are equal. Without loss of generality assumes that X is not smaller than Y, and then we find this Kloppen upset. So not only we separated them with Kloppens, but also with upsets. Well, I mean, at least we separated them with Kloppens, right? Because this is exactly what total separation requires. So indeed, Priestley separation implies total separation. And so underlying set of Priestley space is a stone space. Now let's look at a few examples of Priestley spaces. Now, one thing, why Priestley spaces, why I find it nice and easy to work with Priestley spaces, because you can draw them, because they're based on a poset. So a lot of things, so they are very geometric, right? We can use geometric intuition to think about that. So let's take what is called the Alexandrov compactification of natural numbers. So this is, we take a discrete set, countable discrete set with an extra compactification point. And well, the Kloppen set, so this is well known to be a stone space. And what's the topology there? Finite subsets of n and cofinite subsets of n together with omega. Right? These are Kloppen sets of this stone space. And now we say that, what's this? So we say, let's draw it. So we take, this is my n, right? So 0, 1, 2, and so on. And we say that let every one of them is smaller than omega. So I don't assume that I have an order of natural numbers. So I think of n as just a discrete set, right? Just for convenience, I just call them the names of natural numbers. And yeah, this is omega 0, 1, 2, and so on. Okay, so I claim, so every point here is Kloppen, is isolated point, because every u finite is n. So in particular 1, 0, 2, they're all Kloppen sets. So now I claim that this is a Priestley space. It satisfies the Priestley separation axiom. Maybe as an exercise to the students, why is that? Who could tell me why does this space satisfies the Priestley separation axiom? So we need to look at x and y such that x is not smaller than y and find a Kloppen upset that separates them. So for example, 1 and 2, 1 is not smaller than 2. What will be the Kloppen upset that separates 1 and 2?
Sir, if we contain omega and any set that contains the omega, that will
Yes.
also contain, I mean, the cofinite sense, we can consider the set as the, you're drawing it. We
For
can
example,
say,
1 and every, and this, right? So every, some cofinite set containing
cofinite,
omega, also containing 1 and not containing 2, right? Indeed, that's correct. And
the sir, compactness is already provided because
compact, yeah, good point. Compactness provided because we assume that we know that it's a stone space. Now we also need to show that another case, so omega is also not smaller, less than or equal than some natural number n, right? So we need to also separate omega from this. But that should be also easy, right? Because take any cofinite subset which contains omega and doesn't contain n, right? So everything beyond n, and that will be the cofinite. Okay, good. So indeed, this is an example of a Priestley space. So it's not so difficult to construct such examples. What else we can even do, and this is important because. Okay, well, I'm saying why is this? We can also consider the different order, put it upside down, and we'll see when we'll talk about the Sakia spaces, this will make a difference. So one of them will be in a Sakia space, the other not. But for Priestley, it doesn't make. So now I'm just putting, so these are 0, 1, and so on, and I put omega underneath everything. So this is 1, 2. If we put omega underneath, I'll leave you to check. It's not difficult to show again that this is a Priestley space. Again, 1 and 2, you could separate Kloppen upset 1 or 2, and with omega, you could also separate them with Priestley, again, finite Kloppen sets. Also, as an exercise, I could take like standard order natural numbers, transitive one, and put omega on top. This is yet another example of a Priestley space. If x is not smaller than y, then I can always find the Kloppen upset that contains x and does not contain y. I leave it to you to check the details. The other way around now, natural numbers upside down and omega at the bottom. Again, this is again a distributive lattice because again, sorry, is this again a Priestley space? Because again, you could check that the Priestley separation axiom is satisfied. Right, so we see in general by playing around with this Alexandrov compactification of natural numbers, you could get many interesting examples and also many good counterexamples. Okay, so if you want to look for some counterexample, which is not finite, I advise you to often take the Alexandrov compactification of n and then play around with that. Okay, so this is basically what I've been talking about. Now, we get some intuition of Priestley spaces. Now I claim that if we have a Priestley space, if we take Kloppen upsets, so those Kloppen sets which are also upsets of X, they form a distributive lattice. So this collection forms a distributive lattice. I leave it as an easy exercise. So because what is there to check? Well, finite union and infinite intersection of Kloppens are Kloppens. And in fact, even arbitrary unions and arbitrary intersection of upsets are upsets. So, and then distributivity is also checked trivially. X and empty set, they are Kloppen upsets. So we have. So in terms of duality, if you like, so you could think of it that here we have Priestley spaces. Okay. Here we have a distributed, so the category of Priestley spaces, which I'll define later. We have category of distributive lattices, and on objects, not on one, on objects, this Klopp up, sorry, Klopp up, it forms a functor from Priestley to distributive lattice. But on objects, which we haven't talked about morphism. And this will be, now the question is, given a distributive lattice, and I apologize, so before I called it A, now because it's distributive now from now on, I'll be calling it D. Hopefully it will not generate any confusion. So for a distributive lattice, so the other way around, how to go from a distributive lattice to a Priestley space? Well, we basically already underlined this. So let XD be set of all prime filters. We define an order. So prime filter, one prime filter is less than the other if it's order is inclusion. And we define this patch topologies that I talked about. So for every A, we take phi of A, and then we generate it with its complements. Yeah, sorry, here again, I use different notation. I say, instead of phi A C, I write here X minus phi of A, which is a complement of phi of A. And as we said, that this is unions of finite intersections of that. So now my goal is to show that what I get is a Priestley space. Okay, and then I'm done, at least then I have these two functors. And also, well, we'll show that this also leads to a representation. Okay, why is this a Priestley space? So what's there to check? So we need to check that XD is compact and satisfies Priestley separation axiom. Let's show that it satisfies Priestley separation axiom first, and this will be rather easy. So suppose X is not, and X and Y are prime filters, right? So suppose X is not smaller than Y, that means that X is not included in Y. That means that there exists an element in X which is not in Y. But that means now that A is not in Y is if and only if Y is not in phi of A. And this means that X is in phi of A. So we basically have this. Okay, so we separated X and Y with phi of A. Now, finally, I claim that phi of A, we already showed that it's an upset. And we also, the way we defined topology, let's look at this. This is important. This is not the case in spectral spaces, and this is what Marcus will talk about. Phi of A's become compact opens in spectral topology. But here, phi of A is Kloppen because I took phi of A's and their complement. So phi of A is open, and I forced that its complement is also open. So phi of A is Kloppen. So I separated X and Y by a Kloppen upset. This is exactly what Priestley separation axiom tells us. Okay. Now for compactness. Usually compactness are more difficult to prove, but also quite elegant. And this is something also you've seen in the Stone case. So first of all, we need to show that from every compacting means that from every covering, we can get finite subcovering. Okay? Now, any covering here means that we need to take intersections of these elements and then their union. Quite a monster, right? So it's not so easy to work with this. However, what saves us is that this well-known result in topology, which is called Alexander's subbase lemma, which uses the axiom of choice, which tells us that to show that a space X is compact, it's enough to take the covering from the subbases. So we don't need to take the intersections. It's just enough to work with the subbases. That simplifies our task because I can think of XD as just union of phi of A's and their complements. No intersections. No their intersections and their union. Okay, well, this is something that we already used early on. So the prime filter theorem, if a filter and ideal have the empty intersection, then there exists a prime filter which contains this filter and has the empty intersection with the ideal. This is true for Boolean algebras. This is also true for distributed lattices. Now, what we'll do next, we'll just generate a filter with BJs and generate an ideal with AIs. So take the least ideal which contains AIs and take the least filter that contains BJs. In other terms, we are taking, so this is a good exercise to check that. That means that you are taking midts of elements of BJs and everything above it. This is what generating a filter means. And in the case of ideals, you take the joins and then take everything underneath. Okay, so we have this filter and ideal. We are distinguishing two cases. They are not disjoint and they're disjoint. There's this filter and ideal and they're not disjoint. So what does this mean? That they exist A, which is in F and also in I. So that means, as I said, being in F means that A is above some meet of BK, P of P1, so on BKs. And being here means that it's below this join. Okay, so this is because A is in I, and this is because A is in F. But now, well, we prove that phi is a lattice morphism, so in particular it's monotone. So applying phi here, so that means that phi of this is subset of phi of z. And then we also prove that phi commutes with meets, right? So it's a homomorphism. So from here we get that phi B1 so on BK is a subset of phi A1 so on AN. But this is now, this is because of that. But now note that what do we get now from this? What is that? So if A is a subset of B, it means that not A union B is everything. So everything is X minus this union that part. So this union, the complement of that is everything. And here again, we use some, because these are sets, use some De Morgan laws. So this in set minus commutes with intersection. And then finally we get that XD equals to a finite, and we are done. We obtained that X is so from the covering, we obtained a finite subcovering, right? From this covering, we got finite subcovering. So this is exactly what we wanted to prove. Okay, now another case to consider, that F prime and I are disjoint. But then by the prime filter theorem, there exists a prime filter F prime, which extends F and has disjoint intersection with I. So then this F prime, because it's a prime filter, belongs to XD. But now I claim that it does not belong to any of this, neither AIs nor BJs. Because if F prime is in here, then it should belong to one of the phi of AIs. That means that AI should be here. but we just picked it exactly so. So F has disjoint empty intersection with I, so it doesn't contain any AIs. And F belongs to this. That means that Bj does not belong to F prime. So F prime is in XT, but it does not contain any AI and any Bj. So it's here, but not there. Contradiction. So F and I cannot have empty intersection. So we are in this case, and we already showed that we have finite subcovering. Okay, quite an elegant proof, also similar to how you prove compactness in the stone case, but now we also, in addition, we use Alexander subbase lemma, and we work with filters and ideals. We generate both filter and ideal, filter with BJs and ideal with AIs. Are there any questions about this? Was this clear? Or if it was too fast, you could always, I mean, we'll upload the slides, so you could already always follow the slides. So we proved, yeah, are there any questions?
I can't see anyone has any question from offline participants.
Okay. Okay, now, so we get that what we wanted, that we got that these prime filters form a Priestley space. And now I want to show that, yeah, so I want to show that phi is an isomorphism. Phi of A, we know it's a Kloppen upset. So basically, the range of phi is in here. So the only thing is to show that it's surjective, right? That every Kloppen upset has a shape phi of A. Here, well, I have a proof of this in the okay, injectivity we already showed, so this is a proof I showed you, so I can skip. Now for surjectivity, we need to show that every U Kloppen upset is phi of A. I'll be a bit so we want to show that every Kloppen upset is a union of elements of the shape phi of AI. This requires some argument, which is now, I'll skip it. You need to use Priestley separation axiom a few times. Well, as you see, and this is kind of standard view, and compactness. Priestley separation and compactness, right, as you see. I'll skip this, but if you are interested, please you feel free to follow this argument, right? And so so we get so with this we get that U is a union of yeah. So we prove that U is the union of phi AIs. So this is a proof that I skipped. Now, well, U is a Kloppen upset. So in particular, it's Kloppen. So now we use compactness. So because it's Kloppen, it's closed. Because it's closed, it's compact. So the standard argument, because it's compact, this union is F. So if U is equal to this, then U is equal to the finite. So it's in fact union of finitely many phi AIs. And finally, we use the fact that phi is a homomorphism. So U equals phi A1 join AK. But this proves surjectivity because this is the element A. So U here is phi of A, where A is this join. So again, we proved that every Kloppen upset is phi of something, phi of some element A. And this is basically proves our representation and also well, shows one direction of our duality on morphism. So D is isomorphic to, so what did we do? From D, we went to XD, so we went to Priestley space, and then we came back. So if you want, so here we have D of DL, here we have Priestley. So we came somehow, sometimes this is called specs for spectrum. So this Priestley dual, sometimes it's called the dual of D, It also could be called spectrum of T. So from DL, we went to spectrum to here, and then we went back with plop up. Notation, plop up. And this, and I came and we see that phi shows that this is an isomorphism. So I started, came back, and I came back to an isomorphism. This is one part of the duality on objects. The other way around, if you start here with a Priestley space, you go to clop up and you come back to a Priestley space corresponding to this distributive lattice. What you need to show that what you come back to is isomorphic to the one. So as a Priestley space, it's isomorphic to it. So again, this is also was discussing the case of stone spaces. So this map, which is an isomorphism from here to there. So this is my epsilon.
Nick,
Yeah.
so can you compare it with stone duality? Like you will have a forgetful functor to stone spaces. You said that every Priestley space is a stone space, right?
Yes.
So is it true that every stone space also has a less equal relation which satisfies Priestley separation axiom? Is there a canonical?
Well, equality, right? So
okay, just equality, right?
Equality. And now it's and in case of algebraically, you are taking a Boolean algebra over this distributive lattice. You are generating a Boolean algebra over distributive lattice. That would be the dual of your stone space.
Okay. Thanks.
Yeah, good question. Thanks. So we define this epsilon, and again, I don't want to show, but at least one thing maybe I still might want to show. So we define that. So we take all the Kloppen upsets, which contain point x, and then we want to show that x is at least that they are isomorphic. These two spaces are isomorphic as orders. So that x is less than or equal than y if and only if epsilon x is a subset of epsilon of y. And this maybe we could try to show, because then we'll see what properties we're using again. So what is this is all prime filters here. So epsilon x, it's a prime filter. So every Kloppen sets containing S form a prime filter. This is easy to show, because if x belongs to U union V, x belongs to U, or x belongs to V. And this is exactly means that epsilon x is a prime filter. Now, let's see. Suppose x is smaller than y. Y would maybe question, so this direction. How would you show this direction? Why is this true? So x is smaller than y, then epsilon x, so take U in here. So U belongs to epsilon x. And let's, x, this is small x, sorry. And then this is equivalent. This implies that x belongs to U. Okay, well, and then, yeah, so I ask you, but it's very easy, right? Then x is smaller than y, U is an upset. So from here we get that y is also in U. And that implies that U belongs to epsilon of y. Okay, so this direction we showed. Now, question to the audience: how would you show the other direction? Why does the other direction help? So why right-hand side implies the left-hand side? Yeah.
Suppose that x is not less than equal to y, then there exists a Kloppen upset which contains x but does not contain y. So that set will be an epsilonless, but it will not be.
Unfortunately, I don't hear you very well, I'm afraid. Maybe someone could repeat somehow the
Please
sound.
repeat again. Yeah, that will be better, I guess. Could you please repeat your question again?
Oh, the question is why does the other inclusion hold? So epsilon x upset epsilon y. Why does it imply x is less than or equal than y? And here's, let me give you a hint. Let's do it by contraposition. Let's show that x is not less than or equal than y.
There is some answer from the offline audience.
Okay, yeah.
Yeah.
So that's what I had in mind to do from contraposition.
Yeah, we do contraposition. And then how do we know that this is true?
Wait. Yeah, there is answer from. Yeah.
So because then we have a Clopen set which contains x but not contains y.
Yeah.
So
Yeah.
it will be in epsilon x but not in epsilon y.
Yeah. So a bit of an offensive question, right? It's too simple, but not Clopen, but Clopen upset, right? So this is exactly the Priestley separation axiom, right? Spelling it. Priestley separation axiom gives us a Clopen upset U, which is contains x, not y, but this is exactly, this tells me that this inclusion is that epsilon x is not. So we see that to show this isomorphic kind of Priestley separation axiom is exactly what we need to show that you come back to the isomorphic one. And this kind of axioms also show up in more modern dualities that are considered also these days. Again, you always need something like that. So if x is not smaller than y, then you want to separate them with kind of good Clopen sets. Okay. Oh, plenty of time. We still have half an hour, am I right?
Yeah.
Okay, very good. Now, oh, in fact, oops, I think well, I haven't formulated do I have it? No. So how would we formulate now Priestley representation theorem that for every distributive lattice is isomorphic to Clopen upsets of some Priestley space XD. That's what we proved. Right, so we constructed XD, which is a Priestley space, and we showed that this map phi is an isomorphism. So every D is isomorphic to Clopen up XD. So we proved it in all the detail. Now I claim that the following one, like in the case of stone spaces, like in case of Boolean algebra, the following easy corollary we get for free. Every finite distributive lattice is isomorphic to the lattice of upsets of some finite poset. And again, question to the audience, why, just to make sure that you are still with me, how would you get, why does this follow from what we already done? Here you need to use one fact that's probably already seen in case of stone spaces. Every finite stone space is discrete. Discrete means that every set is Clopen. In fact, every finite T1 space from the T1 separation axioms that you've seen in Purvita's class is already discrete. So Clopen, so every finite distributed is isomorphic to Clopen upsets of the corresponding space X, right? This is what we proved. But X is finite, so Clopen upsets is the same as upsets because every set is Clopen in the finite case. So I have this formula, this representation, finite representation. So we don't need any topology. So that's also quite convenient. Yeah, maybe as an, I don't know whether we want to do, well, maybe as in one simple exercise we could do. So if we, for example, if we start with this distributive lattice, what will be its dual Priestley space? So we need to look at all, yeah, normally you could do something then analogs of atoms, which are conjoint irreducible elements, but because I haven't talked about that, let's see. So this is my 5-element distributive lattice. Let's look at all prime filters there. And I claim that prime filters here are, so 1 and 0. I claim that this is a prime filter. this is a prime filter, and this is a prime filter. So I get this picture. And this is not a prime filter because A join B is there, but neither A nor B is there. Everything is not prime filter because it's not proper. So basically looking at prime filters of this five element distributive lattice, we get kind of this picture. Now, if we want to take all Kloppen upsets, but Kloppen is all upsets here. Again, what are the upsets? So everything, the empty set, this upset, then this is also an upset, and that's an upset. So this is exactly what we get, and we get back our 5 elements, right? So and that's what we proved, right? So if you go from a finite lattice, distributive lattice, to corresponding poset and then back, you get the same thing. So this is a finite version of this representation / duality. Now, finally, let's talk a bit about morphisms, right? Because the duality is a duality of categories. So we need to define what the category of Priestley spaces is, and Priestley morphism. So a Priestley morphism is a map between two Priestley spaces, which is continuous. So that means that pre-image of a Kloppen set is Kloppen, and which is order preserving, which means this, or monotone. So x smaller than y implies fx is smaller than fy. So, okay, so this is definition of a Priestley morphism. And then we get that if f is a Priestley morphism, then f star, which is defined on Kloppen upset, again, maybe I could, this is exactly why we have a duality. So if we have a map from x to y, with f, then we define f star, but now already from or I could write x and y. But it reverses. So this map now goes in this direction. And that's why exactly why we have duality. So our functor is contravariant, not covariant. It reverses the errors. Now let's see, f star is, we define it as a pre-image. So take Kloppen upset, take its pre-image. And I claim that this is, and it's an easy exercise, this is well defined. The inverse image of Kloppen is Kloppen. This is given by continuity, and it's easy to check that that this condition guarantees that inverse image of an upset is an upset. So inverse image of a Kloppen upset is a Kloppen upset. Okay, and so that gives us the correspondence, how to go from Priestley morphism to yeah, and it's easy to see f. This is something to remember. F inverse usually commutes with everything, commutes with intersections, commutes with unions, arbitrary intersections, arbitrary unions, and also commutes with complement. So this is a bounded lattice morphism because it's a lattice morphism is commute with intersections and unions. So I leave it as an exercise to check. The other way around, if we have two distributive lattices and a bounded lattice morphism, then we define corresponding one again, it reverses. From XB, so the Priestley space of B correspond to the Priestley space of A. How do we define it? Again, similarly to the Stone case. We take a prime filter and we take its inverse image. So under a homomorphism, a bounded lattice morphism, inverse image of a prime filter is a prime filter, and we need to check, so this is, I guess, also an exercise. Checks that H star defined like this is in fact a Priestley morphism. So it's order preserving and continuous. Again, not very difficult to check. So this gives us that, okay, now let's define this category, Priestley of the category of Priestley spaces and Priestley morphism. And we get, now I didn't prove dualities of this and that, so I described this morphism, right, between Priestley and DL. Now, basically, this is another exercise. to show that basically the way we decide, we defined the morphisms between the factors between these categories is gives us dual equivalence. Okay, we did check it on objects, but for morphisms, this is final thing is to do is for morphisms. This would be a good exercise because I believe you also had a course on category theory, right? So you will need to, at this school, so you need to also recall some basic definitions from there and apply them here. Okay. Yeah, so this will also leave as an exercise. Are there any questions for now?
No questions from offline participants.
Okay, good.
Oh,
So
one question is there. Yeah.
okay.
Please, just a moment. You need a mic, otherwise he cannot.
Yeah, unfortunately, I cannot hear.
Yeah. Now,
So can you go to the slide of definition of Priestley morphism?
Yes. So order preserving and continuous.
Yeah.
Clear. Okay.
And
I have one question. So you said that continuous means pre-image of a Klopen set is Klopen. I think isn't that too weak? Or
for this space in general, you are right. No, but for stone spaces, it's equivalent because Klopens form a basis.
Okay.
So in general, you're right because you may not have any Klopens at all, right? So for example, on the real line, no Klopens. So every map is continuous. Every map is such inverse image of Klopen. But yeah, for stone spaces, it's equivalent. Yeah, good point.
Okay. Thanks.
And yeah, so this comes now with its own duality dictionary. Again, this is how you, for example, filter now becomes not closed set but closed upset because it becomes a filter, a set corresponding to a filter will be intersection of phi of a's. Phi of a is a Klopen upset, so the intersection is a closed upset. Ideals become open upsets because this will be union of phi of a. And so on. Maybe I don't want to spend, but again, we have this duality dictionary, which is very helpful. Again, gives us a way to move from algebra, like lattices to order topological spaces, use our topological intuition, and come back. And at the very end, I would like to give one application of this for how to use. Again, I'm pretty sure probably you don't need duality for this. I mean, whatever I'm going to show you probably could be done without duality, but I'll try to illustrate it using the duality. This is the property of amalgamation, and I'm afraid again I need to draw this with a bit of ugly diagram. So what's amalgamation? So a class of algebras, so a distributive lattice has amalgamation property if the following is true. For every A, B, and C, if A is embedded into B, and A is embedded into C, then there exists D such that unique D such that we have, well, this should be dotted, that we have embeddings here. Something like similar to push outs, right? Or in categories here, push outs or pullbacks. I guess push outs, right? Yes. But unlike push outs, this must be an embedding. Now, well, I don't know, Marcus, how algebraically probably it could be done, right? But now I'm going to illustrate it, how to do it well immediately.
There is a question, Nick.
Yeah.
There is a question from the audience.
Yes. Unfortunately, I do not hear.
Can you hear now? Please.
Hello, sir. A is any means is a distributive lattice or
A, B, and C are all distributive lattices, and D is also a distributive lattice.
okay.
Now again, let's use duality to show this. So now let's dualize everything. Okay, and there are a few things that I'm showing. So let's take XA, which is dual of A, dual space of A, so Priestley space. Take XB here, and take XC. And now this embedding, so this again using duality dictionary, embedding corresponds to so this is distributive lattice embedding, so it corresponds to Priestley morphism, but it also can be easily shown that if this is injective, then this is surjective. So we have here surjective now. So we need to find now a Priestley space such that now we are talking about the another diagram, and now here where this is more similar to pullback, right? And so what we are going to do here, so we still need to use some properties. So we will take, this is kind of standard procedure in, I guess, what's good. We'll take the product of XB and XC. From there, we have projections there. And then we take, say, Y such that Y is equal those pairs, those pairs, X and Y. And I want to call this map, so F and G, such that Fx equals to Gy. And now I claim that, first of all, there are a few things to be checked, right? So first, that if you have two Priestley spaces, their product is still a Priestley space. That can be checked. Second, I claim that Y is a closed subset of that. That's also, I mean, we might put this as a tutorial exercise. Again, all this need checking, but then they're not very difficult. Because this is a closed set, closed subset of a Priestley space is a Priestley space. So this is a Priestley space. And then this diagram commutes, because if you go from X, so X, I exactly picked those pairs X and Y such that this commutes. Oh yeah, so of course in the when I said in our amalgamation, this should commute. So we define it exactly in such a way that this commutes. And so this shows this Y is exactly the one that you want to show. So in summary, what did we do? We had a question about algebra, that whether some D exists. I translated it in terms of spaces, and here it was easy, relatively easy to show that I can find this Y, so this D exists, right? So you see that you are immediately moving back and forth between algebra and duality as you like, right? And so this way you prove that distributive lattices has amalgamation property. Final thing to say, amalgamation also plays an interesting role in Hating algebra. So if I have time, I'll discuss it, although the proofs there are not as simple as that. However, in the Hating case, a variety of Hating algebras, good class of Hating algebras has amalgamation property if and only if the corresponding logic, so we said logic, algebra, and duality. So even only if the corresponding logic has interpolation property. So this is how you see kind of this triangle at play. So on the logical side, I am asking the question, which intermediate logic, so which extensions of intuitionistic logic have the property of interpolation? Purely, again, I'm not defining it, but probably many of you seen it in some basic logic courses, interpolation. Okay, so that's a question. I'm translating it into algebraic sense because that means that this question is which varieties of Hating algebras, again, I haven't defined what variety is. Let's think of it like good class, equationally definable classes that correspond to logic. Which varieties of Hating algebras have an amalgamation property? So this property. Again, it's hard to answer this. Then you move to the duality side, right? And here you ask which corresponding spaces for which spaces this diagram commutes. So this one, maybe the dualities corresponds to Priestley analog of Hating algebras, which are kind of cyclic spaces. We solve it here, go back, so we kind of have this triangle again. On the spatial, so let me call it, say, topology. On the topological side, or order topological, we solve this using our spatial intuition. We translate it here and then back, and this gives us a full characterization of intermediate logics that have interpolation property. So we have this triangle at work. Okay, maybe it's a good time to stop now, but we still have about 10 minutes, so I would be happy to answer any questions that you may have.
Thank you so much for conducting such an interactive session throughout your lecture.
Thank you.
So is there any question you can discuss with Nick, because we do have 10 more minutes, right? Yeah, Prashanjit. Yeah.
Should I erase this?
Sir, for any non-distributed lattice or in bounded lattice, we have a some duality results proved by Hartung or Hartungs and someone done. So, sir, for bounded lattice, what can we say about amalgamation problem? That for bounded lattice, we can find some D using that duality results.
That's a good question. I'm not so amalgamation in lattices. I think it's been studied, but I'm not sure. I don't think there's a full characterization. At least I'm not fully aware. Marcus, are you aware of amalgamation in lattices?
I mean, which lattices now? All lattices or
all varieties of lattices, I presume.
For bounded lattices.
Bounded
Bounded lattices.
About bounded.
I think, I mean, the category is complete and co-complete. So one has these push outs,
yeah.
But I mean, how to compute it? This is kind of difficult. And indeed, on the topological side, this corresponds to a fairly simple operation. So it is kind of this example is very good, kind of because this is it's kind of, you can draw pictures and you can really think about this in a geometric way. So I don't really know if this amalgamation for lattices.
For varieties, I mean, it might which full characterization may not exist. But let me answer your first question about duality for lattices exists. Many different dualities exist, and in fact, my favorite one, at least I'm more. Recently, there's been a new wave of dualities, if you like, which started from even for Boolean algebras, but that was motivation was to do it choice-free there without axiom of choice. I like this new duality, and we have a very recent paper where we illustrate that this duality is also useful for various things. For example, we prove using this duality kind of analog of Salquist theory, which is the theory of model logic, and also we prove an analog of Baker and Hales's result, which says that every variety of lattices is closed under ideal completions. So this duality works like that. So instead of, if lattice is non-distributive, prime filters are not enough. You cannot, I mean, prime filters are enough only when you work with distributive lattices. But you take all filters, all proper filters. It's a huge, much bigger, right? But still, some of the techniques that work with prime filters, at least this is we try to demonstrate, and we believe that some of the techniques still can be adopted. So I'm now currently more of a fan, if you like, of this new duality where you take all filters and not pair filter ideal pairs or so on. But again, I don't know whether this could help with amalgamation if it's still open in the variety of lattices.
I think for lattices, one also looks at congruences, right?
Yes.
And then this is actually, that's a topology itself, right? So the congruences of a lattice forms themselves a topology, and it's actually it's actually coming from a spectral space. So you can actually go back to the distributive case.
Yes.
So that's also a path. I might say something about this.
Yes.
I don't know. We'll see.
Yeah, maybe to finish. Well, are there any questions? So let me just put some.
Yeah, I have one. So you mentioned that Priestley duality corresponds to positive logic. So can you say something more about it?
Yes, but yeah, that's not because of Priestley, but because of distributive. Because think of what's a distributive lattice. It's a Boolean algebra without a negation, roughly, right? So it's a kind of if you add negation to distributive lattice, you get Boolean algebra. So on the logical side, it's classical logic minus negation, and that's positive logic.
Okay, thanks.
Yeah. So just to put this, I think Marcus will be talking about. So this is what we discussed today: connection between distributive lattices and Priestley spaces. And today, later on, I suppose Marcus will be talking about this connection.
Indeed.
So, and we'll see that there are two categories, very similar but still different. Well, spectral spaces and Priestley spaces, and well, they give both duality for distributive lattices. This one again, this one has topology and order. This one just has topology. That's what you'll see later today.
Any more questions from the online participants?
And maybe to add to what Amit's question, yeah, positive logic as such, maybe it's less interesting. Why? Because distributive lattice is, well, it has no subvariety. It's just, yeah, very simple. There's one positive logic, say, like the one of distributive lattices. However, for example, as soon as you add, say, model operators, distributive lattices with operators now become very, very complicated and difficult. So, and this corresponds to positive model logic, right? So as opposed to, say, classical model logic, where you have Boolean algebra with an operator. And in fact, distributive lattice with an operator is more difficult than considered to be, because you could have box, you could have diamond, you could have either or the other, or together. So it's much more.
Oh, that means you mean that box and, because we already know that box and diamond operators are dual to each other. So as the negation is not there in the positive logic, so I will face some difficulties there.
Yes, so then you could consider D and B box, or D and diamond separately, or together, but then you need to have these Dahn axioms, which tells you, I mean, you can, their connection needs to be expressed without negation, and that could be done. This is called Dahn's axioms. But yeah, interesting question, right? How would you express this? And there's kind of famous axioms of this positive model logic.
Mm-hmm.
Yeah, I asked this question mainly because this is also a good motivation for studying fragments of logic.
Yeah.
Yes.
Yeah.
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 Yes.
True.
Yeah.
Because of the short duration of this school, I cannot cover the full first order logic. I will only cover a small fragment. So this is a positive logic is a fragment of classical propositional logic. In that sense, this is easy to motivate.
Yeah.
Yes, exactly. And positive model logic is a fragment of classical model logic. And in many ways, it's more difficult. So it's also not true that fragment is simpler. Fragment could be more complicated. If you drop negations, things become more difficult.
Right.
Yeah, that's good.
Thanks a lot.
Let me say, so why? This is what Marcus will talk about. Phi of A's, right? I mean, why are they no longer clopin, right? Because you don't have a negation. If I had a negation, then I would have that phi of not A, or let's see, phi of not A equals to phi of A complement. So a complement, phi of A is open, and its complement is also open because of this negation in the case of Boolean algebras. Now I do not have a negation, and that's exactly why phi A is no longer clopin. Right? So
I lost negation and I lost this stone representation for Boolean algebras. Okay, and yeah, so my plan is at the next lecture to talk about hating algebras and the second duality. That will be tomorrow. So how to generalize Priestley duality. And for beta, so I need to define hating algebras, right? So
yeah.
Okay, good.
And it's really good because we already saw that something actually missing the negation totally, and classical logic had negation with its full with all the axioms of it. And in I mean hating algebra, we are going to see some different type of negation. So that's good, actually, good continuation. Okay, thanks a lot for your such a nice lecture. And I would like to announce something for all the participants and also for the offline participants. One is that, like, it's already announced before lunch. It's about that at 5:15 we are planning to take a photo with yeah, just after Marcus's lecture. So like I actually request all of my online participants together with all the speakers, please be present and turn on your video at this moment, and we are going to capture our offline participants together with online participants. So kind of a hybrid photo we are going to capture. And the second one is for our offline participants. So we are planning to arrange some dinner for today. So we are planning to meet at 8 o'clock, around 8 o'clock at Hall 7. So please be present there. We will have a dinner all together. Okay,
can you make a picture of the dinner so that we see what we are missing? It's probably very delicious, right?
So we will do that.
Okay.
Sure. Hybrid dinner.
You are most welcome to join us, and we
would like
to welcome
maybe,
you to India and feed Indian food.
Can send some over. Yes.
Yeah. Okay, so we do have a tea break right now, without tea, of course. So for it's 15 minutes, right? So we are going to meet at like 3:45, and please be here by 3:42 at least. Okay, so we are going to start it sharp at 3:45, and we are going to listen to Professor Marcus Tressl. Thank you so much. Okay.
Thanks. See you.
Yeah, Marcus. Okay. Yes.
Yeah. Yes.
Say something.
No. Just make a coffee now, and then.
Okay. Sure.
Then I'm back. Okay. Bye.
Hello, Marcus. Are you around?
Yes, I'm here.
We are just waiting for some technician to raise the volume. I think your accent together with low volume, it's difficult to hear.
Oh, okay. Wait, but maybe, wait. This might actually be, maybe this is my problem. Is it better?
I hear it okay, actually.
Okay. No, I mean, we are sitting in a large room, so maybe we need to raise the volume.
Okay.
And I'm used to the accent. Some people are not.
Right. Okay.
Well, in any case, I can do the introduction part. So a very warm welcome to the last session of the 4th day. It's my great pleasure to have Professor Marcus Tressl here. I have known him for 12 years now, and this is his second time accepting invitation from IIT Kanpur. So his research interests include model theory, algebra, and non-Hausdorff topological spaces. And recently, he has co-authored a book on spectral spaces. And that's why we invited him to give a talk on spectral spaces. It's very much related to the theme of this school as well. So just give us 1 minute, we'll increase the volume and then we are done. Yeah, Marcus, could you say something, please?
Yeah, hello. I've shared my screen.
Yes. Yes.
Hopefully you can see this.
Thank you. Yes, Marcus, we can start.
Okay. Then I go ahead.
Yeah, sure.
You understand me? If you don't understand me for some reason, just let me know.
I think everybody understands you now.
Okay, good. So thanks a lot for the invitation, and I would maybe also put up thanks to the organizers, Babita Jana and Amit Kuba, for doing such a great job bringing together all these people. And I think it's a great service for young people to learn the subject, and also great service for our subject, right? Kind of to promote this, to offer this to younger people. And it's really organized very smoothly. I can't remember that I've been on an online conference that was somehow done so smoothly. I don't know how you do that, but it was really, these hybrid formats are so complicated, and it must have been a lot of work, I think. So thanks a lot. Okay, so I'm going to talk about spectral spaces. There's one thing. The slides, I have slides, and so now, hang on. The slides of the talk, I put them in the chat. You can, if you open the chat now, you can click on this, and this is exactly the slides I will be talking about. So just that you don't need to you can go back if you want to look up certain things, and there are also references, but I think it's always quite useful to have the slides. Simply if you forget the definition, you can look back on that. Okay, and that's one thing. And right, so we'll be talking about spectral spaces, and this is closely related to what Nick has been talking about. But just to make this clear, I will not really formally rely on what Nick is saying. So in a sense, you can kind of do a tabula rasa, erase what you have just heard, and look at this talk in a sense independently. Of course, I will connect it, but I do not in any way rely on what Nick said. And there will also be a repetition now. Certain amounts of material will be repeated, and but under a different perspective. And this is quite good, I think, that one can look at the subject as the stone duality for distributive lattices from fairly different angles, in my view. And if you want to get kind of into the subject, the realities is that you need to know both sides. And it's really informative to see these two talks in consecutive order. But I'm not really depending on it now. Okay, so here we go. So I'm really kind of coming from topology, and I will first want to talk about this task of representing posets in topology. And as a classical route to stone duality via topology now, this goes as follows. So this is kind of a naive approach. So we are given some poset P, and we want to find a topological space X that has, in the best case, full knowledge about P. So, right, so you want to kind of, well, maybe you can compare this to what we have heard yesterday in one of the talks at the end about this Galois correspondence. So you have a problem about fields, you want to move it into a different context where you then maybe have other tools and a new perspective on this, where you can answer your question. And this one can do with posets as well, and actually with many other algebraic structures. So to make this more concrete, I'm saying it in this form. So we have this poset given, and we want to find a topological space X associated to P, such that there are topological properties of this set that single out a certain poset Q in X, which is isomorphic to P. Right, so you have seen this. We have seen this actually with stone duality yesterday. I put that down, but in a second. But why is this useful? Well, the point is, if you move into this into topological spaces, or in this category of topological spaces, you can now ask geometric questions. For example, you can ask. So we have a space. This space might have certain properties. For example, it might be connected, or it might be locally compact. What does this tell us actually about the poset? Or we can do topological constructions like an algebraic topology, if you have heard this, like suspensions or excisions or gluing of spaces, right? We have kind of a naive geometric synthetic intuition about what's going on with surfaces maybe. And so one can do this in this category of topological spaces and can try to see what does this tell us actually about the poset. And as a matter of fact, okay, so now I'm referring to Nick's talk. I have been here to his talk, sorry. So for there's this amalgamation corresponds to some form of gluing, actually gluing process of gluing topological spaces together. And one can really think in a pictorial way about this and get algebraic information out of the situation. That's why one wants to translate algebra into topology. It's a very naive idea. So you have kind of forms that you do something with it, where you have some intuition and then you translate it back. The properties that I've put down here are in particular interesting because they are, well, the second one maybe, in a space, you can ask local questions, right? So if you think of some surface that you maybe have or some space, then the space might have a difficult structure, but locally it might actually be not too difficult, right? And simply this simple observation enables you to break down on the algebraic side the structure that is maybe a priori complicated into local questions. And this alone is kind of a big thing already, right? Okay, so we'll say maybe a bit more about this later. But to incarnate this philosophy, I'm just referring now to this example of Boolean algebras and stone representation. So this is now an incarnation of this task here, what we on top, what we wanted to do. So we take a Boolean algebra, and then the classical stone representation somehow manufactures a topological space X. How this is now done, now not so important. So there's a topological space, and this topological space has the property that we can topologically identify certain sets, namely Clopen sets, open and closed. And it happens to be the case that this partially ordered set is isomorphic to the given Boolean algebra, right? Okay, so task, this is kind of the task is accomplished here. So we have a kind of we have a purely topological framework where we can talk about this Boolean algebra. So now we can ask local questions. How does this Boolean algebra look? How does this space look locally? And this is a priori a simpler question, right? And I mean, one can rely there on the simple intuition you have about spaces. So when one sees this stone type presentation, when I was a student and I saw this, I saw, oh my God, I have all these ultra filters, and then you do all kind of complicated Greek letters, and looks complicated, but the reality is that the space is an easier object. And this is something that one kind of, you get to this when you work, when you do exercises, when you try to answer questions. So in reality, this is kind of a feature of this presentation in topology, that you can break up the space into smaller pieces in a kind of an intuitive way, and can look at these pieces. This will give you a route to understand your algebraic structure. So that's okay. Philosophy is, of course, kind of my philosophy, but I think many people will agree to this. Right, so this is really the background of this yoga of moving into topology. That it gives you naively a way to break up an a priori complicated structure, or a structure that you don't know, into smaller pieces. Okay, so informally, I should maybe now come a bit more to spectral spaces. So informally, what you have seen for Boolean algebras and Boolean spaces, spectral spaces take on the role of Boolean spaces when we carry out task above for distributive lattices. Okay, this is just that you know where this thing belongs to in the mathematical landscape. But there's one thing that one has to be careful of. Nick mentioned this. These spectral spaces will not be Hausdorff. So I will have to say something about certain non-Hausdorff phenomena, and this can be, at the beginning when you see this, rather irritating, because you're used to the Hausdorff intuition, and it's kind of, it's a strange thing to see at first, but after a while, you will see it's actually not so bad that these spaces are not Hausdorff. And then after a much longer while, you might actually find out it's a good thing that it's not Hausdorff. And, but that's kind of at the moment not really understandable. So I'll come to that in a bit. Maybe I should also say some history. So that Nick mentioned that too, that Stone has actually discovered these spectral spaces. He didn't use the terminology. The terminology came from Hochster in 1969. But then they were not really deployed too much on the lattice theory side. And they were in fact actually first rediscovered or reused by algebraic geometers, Jacobson and Zariski, where these spaces, and this is kind of very crucial to the subject, the spaces appeared first. So they had rings and they attached a space to this ring. And that is a representation space for sheaves, we have heard this, for commutative rings. And this is something is a way how spectral spaces in mathematics appear frequently. They appear as a space before the lattice. And the lattice is actually kind of a complicated object. So in nature, I can say this, in algebra or maybe also in model theory, these spaces come first. Right? And then, and so in logic and lattice theory, they also play an important role that the talk will be about. But if you see this in algebraic geometry, for example, the lattice is the complicated object that one wants to study, and the space is a tool you use to study this lattice. So it's again this philosophy that the space is actually easier. It's just when you learn it, you have to cope with certain formalities that are difficult. Okay, so now maybe I start on the more technical part. Are there any questions? If you have any questions, also of the philosophical form, in particular of the philosophical form, please ask, because a difficulty in this subject is certainly why are we doing it? And if you have any comments here, please let me know. Okay, so I'm going to talk about two non-Hausdorff phenomenons, and one is a specialization relation that has already been talked about by Probita and also in the category tutorials. But I think people and lots of students ask questions about this. So I wanted to give a certain perspective on the specialization relation, which is useful later on. So we take a topological space and now recall, maybe think of the reals, the notion of what it means that you have a sequence and a sequence converges to a point. Okay, so here's a reminder. Take a sequence xn in x and a point y in x. And what does it mean that a sequence converges to y? Well, I'm writing out the standard definition of a convergent sequence in the reals. For every open set U containing y, there's some n in n, such that the xk are in U for all k greater or equal to n, right? That's the definition of a convergent sequence. Now, in a non-Hausdorff space, it can happen that this sequence is constant, right? Okay, this can happen. And what does this definition now say? This definition now says that x actually, this constant sequence x, converges to y. And that's really what one should think about specialization, that you have a point, and this point converges to another point. This is really kind of, it's really coming from this intuition in topology. Right? So if all the xk's here are just the same point, this says that for every open set y, for every open set U containing y, the point x, which is always now the same xn, is in U. Right? This was exactly the definition of specialization, x squiggle y. And I think of the squiggle as x converges to y. So this is just a reformulation now. The definition of that a constant sequence converges to y just means that y is in the closure of the set containing x. And this is, of course, well, the definition is not technically complicated, but the intuition is strange if you work in a Hausdorff space, because in a Hausdorff space, points are closed. Okay. But in general, this is not the case. And so the specialization relation captures convergence, approximation. You approximate x by y or y by x. So now in Probita's talk, she explained that this relation is a partial order, if and only if x is a
Hello?
Yes?
One question. So
Yes.
doesn't it mean that x belongs to y bar? Is it y belongs to x bar or x belongs to y bar?
No, y belongs to x bar. Look, if you look at
y.
you see, if you look at the definition, it says for every open neighborhood U of Y, X is in U.
So X belongs to Y bar, I think.
No, it's the other way around.
The singleton Y.
So what does it mean?
Okay.
What does it mean that Y is in X bar? It means that if you have
every neighborhood of X, but you are not looking at any neighborhood of X here. You're looking at neighborhoods of Y.
Yes, but you see, what does it mean to be in the closure of something? It means that if you have a neighborhood of Y, then it hits the set where it's the closure of. Yeah?
X closure. Okay.
So what is the closure?
Yeah. Okay. I agree. Sorry. Yeah.
Yes?
Sure. Yeah. Thank you.
But, no. I mean, there's.
Every neighborhood of Y.
One needs to meditate about this, right? But I mean, if you look at, it's really, if you think about convergence, this is really the way of thinking about the whole thing. So, by the way, when I make this squiggle here, I'm not saying that X is less or equal to Y or that X is greater or equal to Y. It's just a relation that says X converges to Y, right? So I'm not putting an order on. I'm not seeing this as greater, equal, or less or equal.
Yeah, sure. Okay. Yeah.
If I say partial order, you can order it as you like. I don't mind. The proper way of thinking is that X converges to Y. That's kind of yeah.
Okay. Clear? Yeah. Thank you.
I have a question.
Yes.
So here you are considering the topological spaces not to be T0, right? Because T0 spaces singletons are closed. So in that case, the closure of the singleton X will be just singleton X, and that would not make much.
Wait, hang on. A T0 space, I have recalled the definition here. A T0 space means that if you have 2 points, then there is an open set that distinguishes them. Yeah. This does not mean that if you pick 1 point, that you can distinguish this one from the other one with an open set containing that point. So what you're talking about is a T1 space.
Right. Yeah.
Right.
Yeah.
So one has to be careful. And you're right. This is true. So it's actually equivalent. A T1 space is a space where every point is closed, which means that this set is a singleton. It's just X itself. Okay, I'm actually talking about this at the end of this slide. Yeah, so it's really it's this specialization relation that Pabita talked about. It also popped up in other places, but it's something that one has to digest indeed. We'll do examples. Okay, so again, I'm not putting an order on that. I mean, it is a partial order, but I'm not, I ask you kind of not to think of it as greater or equal or as less or equal. You have the option to do this, but in order to understand the theory, it is kind of, it's not necessary, and I'm not picking a side now. Really think of X converges to Y. And now, well, okay, this is what we just said. A point is called closed if this is a closed set, which means that if X converges to something, so X can only converge to itself, right? And then on the other end, there are what is called generic points. This means I have a point, and if this point if another point converges to this point, then it's actually just the point itself, right? These are both ends of the partial order. So if you want to see the partial order is less or equal, the closed points are the maximal points, and the generic points are the minimal points. If you prefer the other order, well, you just do it the other way around. But you see, in topology, these points play a different role. They are kind of their topological nature is different. So this duality that one maybe has can sometimes kind of hiding what's actually going on in the space. This is a rather subtle point. It's, of course, there is a feature that you can swap the point of view. This is a great feature, but then you have actually also swapped the topology. So you're putting yourself into a different context. Okay, so I know that the specialization relation causes problems. So if there are more questions, please ask. Okay, maybe, well, you just interrupt me. Just speak up to speak up for your questions. Okay, so this was one concept. And the other concept is this also something that doesn't exist in the Hausdorff world, but it exists in the T1 world. And this is the concept of irreducible sets. And so I'm calling a topological space irreducible if it is connected in a strong form. And namely, it says, if for all closed sets BC that cover the space, X is B or X is C. And a subset of X, S of X is irreducible if it is irreducible as a subspace. Okay, so let's see what that means. So there's a notion of being connected. A space is connected, and this means that if X is the disjoint union of closed sets, then X is B or X is C. So this connectedness corresponds to what you think of a surface is connected as two components or not. And irreducible is a strengthening of this because the premise is weaker, right? So here I'm actually only asking of X being just a union, does not need to be disjoint. Okay, so that's a concept from non-Hausdorff topology. And so students, maybe some people have seen the Zariski spectra of rings. There, these irreducible sets come up all the time. But okay, I won't touch on this side anyway. So in a Hausdorff space, this does not make much sense because in a Hausdorff space, if you have an irreducible set, then you can have at most one point. Right? This is you can directly, this is from the Hausdorff axiom. And so now let's do an example. And this has to do with the first slide, that if you have an element in a space X, I'm not making any assumption on X, not T0, not anything, then the closure of a point is irreducible. Because if you write X as the union of two sets, A and B, well then, and A and B are closed, then this point has to be in A or it has to be in B. Well, if it's in A, then the closure of this point is everything, right? So, so this set is irreducible. So in particular, the closed sets are all unions of irreducible closed sets. But this union might be infinite in general. Okay, now let's have a look at the second example. Then let's have a look at a finite T0 space. So now I'm putting a separation axiom on T0. And then this first example says that every closed set is a finite union of irreducible and closed sets. Right? And hence every non-empty closed and irreducible set is of the form X bar for some X in X. So what am I saying here? So you take a non-empty closed set. So because the space is finite, it is a finite union of irreducible sets of this form. And now because the set is irreducible, it has to be one of them. And the consequence here is that if you're in a finite T0 space, you can actually recover the points from the lattice of closed sets. Yeah, this is a strange thing that I can give you the following task. I give you a topological space X, and but I don't give it to you as a set plus open sets. I just give you the lattice of closed sets, and then I ask you, can you now give me the space producing this lattice? And this is not always possible. But for finite space, this is possible. And the way you do it, you actually look at the irreducible closed sets. This will give you exactly the point spec. And this is a feature that we will carry over in to spectral spaces. Any questions about this?
Hi, I have a question.
Yes.
So every can we write every closed set as a union of irreducible sets?
You asking why this is true?
No, I'm asking. Okay, it's already written. Okay. I didn't see example.
Yes. So this is the explanation, right? You just take the union of all take the elements in A, take their closures, and A will become the closure of these sets.
Right.
And then if X is finite, then this is of course a finite union because you only have finitely many points. Okay. Good. So these are the first two concepts that are kind of not really don't make sense in the Hausdorff. They make sense, but they are trivial in the Hausdorff context. And so now I can talk about the definition of spectral spaces. And this is now the most complicated slide of my talk. That's kind of the problem with at the beginning with spectral spaces is that the definition is rather complicated. But one needs to realize maybe after a while that a lot of ideas are kind of assembled in this definition, and only later in applications one starts appreciating this. So what I do now is I will put the definition out, and then I will run through the definition in two cases, namely in the case of finite spaces, and then in the case of Hausdorff spaces. And then we will see that it specializes actually to things we have seen already. Okay, so what's the definition? So a spectral space is a topological space, make no assumption about it now whatsoever, and it has four properties. The first one is it's compact and T0. Okay, but that's something maybe we can cope with. The second one says the following, that we look at all the subsets of X that are open and compact. Okay, so remember in the Boolean case, we had this set of sets that are open and closed. And I'm now replacing the closed by compact. And this is in the Hausdorff situation a strange thing, because a compact set in a Hausdorff space is closed. So why am I not writing closed? Well, the point is that in a non-Hausdorff space, compact does not need to does not imply closed. So we'll come to this. I will do an example. We see this shortly much better. So this collection is called K node of X, compact open, KO. And the requirement is that this is the basis of X, the basis of the topology of X. Then condition 3 says that this basis is closed under finite intersections. So that's something in the Boolean case you don't need to do. I come to the Boolean case also shortly. And the last property, these are then all the properties, says exactly what we have seen in the finite case a slide ago. It says that every non-empty closed and irreducible subset of X is actually given in the form we would expect. Okay, so in the finite case, we have seen that this is actually the case, right? So that it somehow tells you that you can recover the space from knowing the closed sets. So I say this again here. So S4 allows this reconstruction process of points from the closed sets. Good. So that's the definition. And as I said, if you now think, oh my God, what is that? And this is complicated, you're right. Yeah, definitions can be the most complicated part of something. And this is certainly the case in this talk. So now let's do examples. So I'm running this definition now again in two instances. Namely, I first assume that X is just a finite topological space, and then I'm looking at what happens to these conditions, and then I have to maybe, in order to make it an example, I have to amend the properties of X. So let's see. If X is a finite space, and the first condition says X has to be compact and T0. Well, compact is not a condition because it's finite, so it's compact anyway. And T0 we need to put down. So we need to amend this. Finite and T0. Okay? What happens to the second condition? We look at all the sets that are open and compact is a basis for X. But again, we are in a finite situation, so all open sets are compact, right? So this is actually not a condition. This is K naught of X. It's just all of the open sets. So this is actually void. This is no condition. And now you actually also see examples of spaces, that's what I said before, where you have an open set that is not compact. So just take a finite space that is not Hausdorff. You have seen tons of it in the tutorials, and take any open set that is not the full space. These sets are compact, but they are generally not closed, right? Okay. What happens with condition 3? K naught of X is closed under finite intersections. Yeah, that's true because we have found out in the finite case, K naught of X is all the open sets. Okay. And S4, we have just done it on the previous slide. Okay. This is also, so the conditions S2, S3, and S4 all disappear. The only thing that remains is T0. So it means all finite T0 spaces are spectral. That's maybe an intuition to hold on one side. And you might remember that, I don't know if this has said something, the category of finite T0 spaces is actually exactly the same as the category of finite posets. Because the only thing you need to know is the specialization relation in these finite spaces, right? And this is now also the same as the category of spectral spaces. I didn't talk about morphisms yet, but okay, maybe on the objects it should be maybe information. Okay, now let's look at the Hausdorff, it's a much loved Hausdorff context. What happens to these conditions when X is a Hausdorff space? So then the first one says X is compact and T0. Well, T0 is anyway because it's Hausdorff, but it's compact. So we need to amend the definition, the example. At least has to be a compact Hausdorff space. But now we see what's going on with S2. And now we are in the Hausdorff context, and now open and compact is open and closed. Because we are inside a compact space, this compact becomes closed. So K naught of X becomes actually the set of Klopen sets. And condition 2 says that the Klopen subsets form a basis. So X is actually Boolean. Okay. Now condition 3, K naught of X is closed under finite intersections. This is now void because the intersection of two Klopen sets is Klopen. So we don't need condition 3. And condition 4 is also void, as we said. So before in a Hausdorff space, irreducible sets are singletons. So conditions 3 and 4 don't play a role. So when X is Hausdorff, spectral means Boolean. Right? And so here you have the slides together. So you have, these are kind of the two extreme ends maybe of spectral spaces, Boolean spaces and finite T0 spaces, where in the Boolean case, there is no specialization and it's all kind of in terms of open and closed sets. And in the finite case, the topology plays no role and it's all given in terms of specialization. And you can see here you can see this Priestley setup. There are these two components that are in the spectral space present. But so now one might go back to Nick's talk and say, I stick with the Priestley spaces. The point now is that the object of a spectral space, what it is as an object, it's just a space. It's just a topological space. And a Priestley space is not a space, right? I think Nick didn't say this. So a Priestley space is not a topological space. It is a Boolean space together with a partial order. Whereas a spectral space is just a topological space, period. And this means that you can study it in the category of topological spaces and do kind of the standard naive operations of excision, gluing, taking products, and these kind of things. Where in the Priestley context, you always need to kind of carry this partial order around. So this is kind of these are kind of the two sides.
Marcus, so we have been using the word stone spaces. I think you mean the same thing when you say Boolean spaces.
Yes, so I'm avoiding the word stone space, because if you ask 3 people what is a stone space, you get 4 answers. So
Okay.
I'm talking about Boolean spaces and about spectral spaces. The terminology stone space is blurred in the literature, so people mean different things about this. Is kind of
okay.
I just call Boolean and spectral.
Okay.
Yeah, one has to be careful. If you look at the literature, then what people mean by stone space, this is not completely well defined in my experience. So Boolean and spectral is just kind of unambiguous. Yeah.
Right. Thanks.
Okay, so now let's do an example. And so in a sense, everything that's coming now is easier. So we'll do an example. You have seen this example in various cases, and then you might get the rest of the talk is kind of to familiarize yourself with the notion. So now an example of a spectral space that is not Boolean, and I'm looking at an infinite set here, and it takes a cofinite topology of T. Okay, this is a reminder that there are also cofinite subsets of T together with the empty set. Okay, I guess you have seen this. And then this space is irreducible, right? So this is not a Hausdorff space, and T is irreducible because the closed subsets are, well, the set itself and also finite sets. So if you write, coming back to using the definition of irreducible, if you want to write T as a union of 2 finite sets or T itself, you can only do this if one of the sets is a T itself, right? So T is an irreducible space. But T violates S4 because there are no specializations actually in this space, right? So there is no point whose closure is the whole space, because this T is actually T1. Every singleton set, every point in T is closed because the complement is cofinite. So T is a T1 space, which is irreducible, and it's not Hausdorff. So this cannot be a spectral space. Well, we add a point. So we add a point and define a new space. This is T together with this red point. Well, then we need to adapt the topology. But we do this only in a minimalistic way. We just add this point to all the cofinite subsets of T. And now we get actually a spectral space. So we have just added a point that corrected this absence of that witnesses that T is irreducible. Okay. And then actually you just check that in fact all open subsets of this space are actually compact, and X is indeed a spectral space. So this you can just by hand verify. It's an exercise. And now I'm drawing the Priestley space, so to speak, of corresponding to this space. Or if you have not been to this talk, what is the specialization relation in this space? It looks like this. So there's the points in T are on top. These are what I call these are the closed points. And the new point is at the bottom. And the new point converges to all these points. That's now also a phenomenon that is only native to non-Hausdorff topology, that a point can specialize to many points, not only to one point. And I can ask now the audience, is this the right picture? Should I draw it upwards or should I draw it downwards, actually? What do you think? So is this specialization, should this be less or equal or should it be greater or equal? So is the picture somehow this way around or the other way around? Any guess? Well, the answer is both are correct. You can see it this way or you can see it the other way. You see, the point here is we have the space is given and you just need to specify what are the closed sets and what are the closed points here and what are the generic points. There's only one generic point. If you want to think this as going upwards or downwards, as you like, the space says that are the closed, these are the closed points, and the other one is the generic point. So this is sometimes one gets confused about this, what is up, what is down. There is no, you want to draw it in some way, but the actual question is what is generic and what is closed. Okay, so now for those who have seen this in algebra maybe, if T is the set of prime numbers, then this is actually the picture of the prime spectrum of the integers. And that's where my intuition actually comes from. And these are the prime ideals of Z, and this is the zero ideal. And the specialization is inclusion of prime ideals. That's why in algebra, maybe you maybe think of this as upwards many times. But there is no right way, it's not correct or wrong. What you should think of, a point converges to another point. Okay, so this is the easiest spectral space, I think, that is not finite and not Boolean. Right? Any questions about this? I'm terribly slow and I might actually not get to anywhere, but okay. You have the slides. Any questions?
Take the complex space of complex numbers.
I take what? The complex numbers?
Complex numbers, and you define the U to be an open set if it is the complement of this finite number of or zero set of a polynomial.
Yes.
Is it, does it satisfy all the properties of your spectral space?
Excellent question. Excellent question. As a matter of fact, this is a fantastic question because this whole example fits exactly to what you are saying. So if I take for T the space that you have just described, I can tell exactly the same story. So the spectrum, this is an irreducible space, but the generic point is missing. And when you add the generic point, this corresponds to the zero ideal in the polynomial ring, you get exactly this picture. So then on top you have the complex numbers, and this is the prime ideal 0. And this was actually how this is exactly the intuition. Thank you, this is a very good question. How these spectral spaces appeared in algebraic geometry. People said we have Zariski closed sets, but there are points missing. There are generic points missing. So we add them. and then they added the prime ideals, and then they got to a spectral space. Exactly. Yeah, very good point.
So your generic point is one point, or the see, there's another way of compactification using the projective space. Are they related?
Yes. That's something different. This is not, you're not passing to the projective space, depending if you know classical algebraic geometry is still Hausdorff. This is not. This is a different way of compactifying the affine plane. That's not the same thing. It's not the projective space.
It's 1 point compactification.
It is not. It's not. I mean, 1 point compactification. One has. It is you add 1 point, but you see, if you do this, for example, in dimension 2, you have to add much more points. Okay. In dimension 2, you would have to add all irreducible curves. But this is maybe now, it's not in the focus of this talk. So I'm really talking about lattices now. It's not you shouldn't think of it as a 1 point compactification. This is too special here, maybe. On the Boolean side, it is a 1 point compactification, is what Nick said, but on the spectral side, it's not. Okay, so there is now a slide which says there are different ways. I have to make a decision now. I have to come. Okay, maybe maybe I stick with this slide, because just to give you some context, because the problem with the spectral spaces is where do they sit in the mathematical landscape. And so there are different ways to describe spectral spaces. And the first one is, okay, just a definition. The second one is what we have just discussed for a minute. It's the same as the prime spectrum of some ring. And ring always means commutative here. And this is how Hochster coined the word spectral space. It comes from the spectrum of a ring. And the third one is, that's what I wanted to talk about, but I'm running out of time. It's the spectrum of a bounded distributive lattice. Okay. 4 is, it's an ordered stone space, also called Priestley space. This is what Nick has been talking about. But I should say again, a Priestley space is not a space. It's a hybrid of a space and an order. Right. So this is it's a different. You're sitting in a different intuition. The fifth one is a purely topological characterization, and it says that X is profinite. So now referring to the category theorist, I don't know if anybody has said this already. A Boolean space can, a fastest way come out to, if you're category theory minded, you can say a Boolean space is a profinite topological space, where the finite spaces are all discrete. And if you drop the discreteness and you just take finite T0 spaces, then spectral spaces are just the co-limits of this. Okay, for those who know that. Item 6, I skipped now. It's linked to model theory, I skipped this now. Okay, so you can look at this, there are references. So these spectral spaces occur in a lot of different contexts, and they normally not occurring via a lattice. And the lattice is normally complicated objects, but we are focusing here on the first 2 items. So the spectral spaces and lattices. Okay, so right. So let me see what we have here. Okay, I have to skip things now. I'm sorry. Okay, so maybe I just go to this. So we take. So I'm now starting with a distributive lattice L, which is always bounded, and this is now what Nick already said. The spectrum of L is a set of all prime filters of L. So we now make a spectral space out of this, and for each A in L, we're looking at a set of all elements in the spectrum containing A. And then there is this Stone representation theorem that says if you take two elements in L, then this operation VL commutes with inf and sub, and it turns it into union and intersection. And this VL map, in Nick's talk, it was called phi. This gives an isomorphism of lattices. So this has now nothing to do with spectral spaces a priori. It's just the old stone representation theorem. And the proof of this theorem is, half of it is self-evident. This is maybe something that I wanted to point out. The proof that this map here has this property is actually the definition of filter and prime filter, you see. The first identity, if you look at this here, VL of A intersected B is VL of A intersected VL of B. If you translate this, it says that these two are equivalent, and this is literally the definition of F is a filter. So there's nothing to prove, it's just self-evident. It's just formulated in a different way. And similarly, the second property, this is literally the definition of a prime filter. And one can actually start by saying, I would like to have such a representation theorem. How do I have to define my objects? And then this will just give you the definition of a prime filter. This is really, there's nothing to prove here. It's just the clever way is, the clever thing is how to define it. And then it's nothing, and then you make kind of this definition. This theorem is sort of a definition, right? Well, not quite. There is one thing that is crucial here, and that this map is injective. This is actually the mathematical content of this statement. The rest is a clever definition. And this, the injectivity is just the prime filter theorem. Nick has commented on this. I can't, no time now to talk about that. Okay, and now I have to finish early. So the spectral topology, not early, I have to finish. I was talking too much about other things. The spectral topology on this spectrum is, you do now exactly the same as you did for Boolean algebras. You declare these VL of A's as open. That also was already shown by Nick. And then you find out the task now is, in the Boolean case, you wanted to find the Boolean algebra again, and this was relatively easy. The answer was take the open and closed sets. And here you find the lattice again by saying these are the open and compact sets. And this is kind of the story or how you arrive at spectral spaces. If you start from distributive lattices. And then you follow basically the classical stone dual thing. Some proofs are a bit more elaborate, but there are no big surprises. So the point is to topologically say which spaces occur here, which brings you back to how is a spectral space defined. So this definition is the one that is kind of gives the answer to the task. So I have to stop now. The slides have much more information. Maybe we can talk in the tutorial tomorrow about this a bit more. But I thought we might focus on more the intuition and the why and how on earth, why on earth are we studying non-Hausdorff topological spaces? Okay, I have to stop, I think.
Marcus, have you prepared only 1 hour talk or 1.5?
Oh.
I say, according to the program, you still have half an hour, Marcus.
Oh, yes, I do. I'm sorry. I have prepared 90 minutes.
Yeah.
Yeah. Sorry. And I still actually have time. Oh, I'm sorry. Oh, okay. Well, okay. I'm very sorry.
Your slides were appropriate. Yeah, the length of the slides was appropriate. You can speak for the rest.
Yeah. Okay, right. I'm sorry. I got the time wrong. This time zone convert. I have a time zone converter, and this is always a half an hour out of time. Okay. Okay. Good. So I can actually. Right. Sorry, I forgot that. I have a bit more time. Okay. First, let's have a coffee. Yeah. So it was very quick. So maybe I go back to, maybe I just remind you of the prime filter theorem. This is all a reminder. Don't need to read this. Just have a look at this. This prime filter theorem says that if you have a filter, I'm in a distributive bounded lattice always. Whenever you see the word lattice, I mean bounded and distributive. It says that if you have a filter and an ideal that are disjoint, then there is a prime filter P of L containing F disjoint from I. Okay, you have heard this now several times. And this theorem has a full topological translation. It says that certain sets are compact. And I want to explain this now. This kind of makes a good link to spectral spaces. So, okay, so we had the representation theorem. Okay, this VL is like Nick's map phi, and it's like in the Boolean algebra case. And now I'm coming back to this here. So I want to show that spec L is a spectral space. So let's say again. So spec L is a set of all prime filters, and the open sets are defined to be by the VL of A, which form a basis. And so it means that every open set is a union, an arbitrary union of VL of A's. And I'm claiming that this is a space where the open and quasi-compact sets are exactly the VL of A's. And that's what I'm going to prove now. And then you will see the meaning of this statement is exactly the prime filter theorem. And this is one of these instances of where we have an algebraic statement. It just becomes a topological statement. Okay, so I'm proving this. Now, one inclusion is that follows from the kind of the obvious part of the representation theorem. So if U is open, then it's a union of sets of the form VL of A by definition. Now, if it's also compact, well, then it's a finite union of these VL of A's, right? But then the easy part of the Stone representation theorem says that VL of A1 union VL of A2 is VL of A1 or A2, right? So you can just join this together, and then you see this open and compact set is actually of the form VL of A for a single A. Okay, but the point is, why is the other inclusion true? And the other inclusion is really, you can prove the prime filter theorem by claiming that the other inclusion here is true. And it's instructive to see what's happening. So now let's see what we need to do. We take an A and L, and we need to show that VL of A, which I now just call V of A, that this is compact. So take some family of basic open sets, take the indexed by elements B, I, and L. And so what I have to do is I have to look at V of A intersected with these complements. So this set here is a closed set, right? It's a complement of an open set. So in order to check that V of A is compact, I have to take a family of closed sets, and I assume it has the finite intersection property. It means that every finite subcollection has non-empty intersection. Yeah? And then I have to show that the intersection of all of them is non-empty. This is the task of showing compactness of a set V of A. Okay, so this is kind of, I assume you've seen this is a reformulation of what compactness is. And now I'm using Stone representation. And the information that this family has the finite intersection property, you need to look at the details, but the details are really easy. What I want to point out is this translates literally into saying that the ideal generated by all these BI does not contain the element A. So I say again, that the family has this finite intersection property translates literally to the property that the element A is not in the ideal generated by the BIs. So you need to check this maybe later. The interesting thing is that this has a translation. And now the stone representation theorem says, the prime filter theorem says there's a prime filter P of L containing A, but not containing any of the BI. That's disjoint from the ideal. And this now on the topological side, on the spatial side, just says that P is a point in the common intersection of all this. So, right, so I'm using the prime filter theorem to show that the V of A are compact. But if I give you the compactness of the V of A, you can also prove the prime filter theorem from it. It's really the topological incarnation of this fundamental theorem. Any person who develops this duality of distributive lattices will use the prime filter theorem. So did Nick in his talk. Okay, so this is, if you want to understand where these open quasi-compact sets come from, this is the place to look at, right? Okay, then there's something else to show, but that's actually not too difficult. And I didn't say about the references. Yeah, this book that I've written, this is in the references. We have all this in detail. But it's also an exercise. At the end of the slides, if you look through the slides, there are exercises, and these exercises fill some of these gaps here. Okay, so now we also need to go the other way, and this I will do quickly because this looks exactly the same as for Boolean spaces. So if we start with a spectral space, we can go now back to the lattice, but this is almost by definition, because the open and quasi-compact sets by definition form a bounded sublattice of the open sets. Now, if you look back at the definition, there's this condition S3, which implies that this is a bounded sublattice of OX. This is basically part of the definition of a space, spectral space. And the map is this, and this is exactly, it looks exactly like for in the stone, in the Boolean situation. And so you have seen this, proof needs to be done, but maybe now not the interesting part. Good. And so now we get to this duality, and I need first to talk about what I haven't done at all about morphisms. And I'm talking about spectral maps first. So for distributive lattices, you have seen this in talks before for lattices. What is a homomorphism between distributive lattices? So this is it's a morphism of posets that preserves finite infima and suprema. So on that side, actually, we know what the homomorphisms are. And now we need to look at what maps are on spectral spaces. And these are not just the continuous maps. Right? So this is now something, this is something that I'll maybe say, oh, okay, so it's not what is called a category series, not a full category of spectral spaces. Yes, that's kind of, this is kind of maybe, I don't know if I want to say it's a weakness, but it is something one has to take care of. So not every continuous map between spectral spaces comes from the induced lattices. So let's go slowly. So we take a map between spectral spaces X and X prime, and this is called spectral if it preserves this open quasi-compactness. So it means that if you take a subset in X prime that is open and compact, then the pre-image, well, it is open because the map is supposed to be continuous, but we are also asking that X is compact. That the pre-image is compact. Okay. So if you have some experience with topology, this has something to do with that the map is proper. But it resembles this in the Hausdorff context, but it is not the same thing. So there on the internet or on Wikipedia, there are things, statements saying spectral maps are proper maps. This is not true. So it's not really proper. It is a condition that just have to add here in order to get to full stone duality. I'm not saying that continuous maps are not interesting, And as a matter of fact, this can actually be quite interesting to compare lattices by having continuous maps between their spectra that are not spectral, right? This gives a connection, but it's much weaker than a lattice homomorphism. This is kind of the feature here, that you are in this, you are purely in the category of topological spaces, and you have all these operations in that well-studied category. Okay, so the point is that you want to have that pre-images give you a map from the K node, from K node X prime to K node X. Good, so now let's see that actually, if you start with a homomorphism of bounded distributive lattices, and you do the spectrum construction, that you get actually a spectral map. So if you have a homomorphism of bounded distributive lattices, you get a map from the spectral, because if you take this should be a P prime. No, it's correct. If you take a prime ideal, a prime filter in L, and you take the pre-image, then you check that this is again a prime filter in L prime. So this is rather direct to verify. That means you get a map from spec L to spec L prime. And then this is also straightforward. It only looks complicated because it's a lot of symbols, but there's not really any depth to this. One checks that if you now take pre-images of the VA here back in here, it will do what you expect it does. So the pre-image of this VL prime A prime under this spec phi map gives you what phi gave you in the first place. And okay, this is hard to dismantle in 1 minute. I'm just saying this formula gives an explicit proof that this map, it is maybe digestible, is actually spectral. So spec phi is spectral, and this K node of spec phi is equivalent. It's not original, but it's not the original map, but it is equivalent in the sense of category theory to the original map. So if you specialize this to Boolean spaces and Boolean algebras, you will just get what you heard in this talk about stone duality for Boolean algebras. Okay, and that's then the summary of the talk so far, or at least the non-philosophical part, that this construction spec is an anti-equivalence between the category of bounded distributive lattices with bounded lattice homomorphisms.
Can you hear me?
Yeah.
Yes. Can you go back to the previous slide?
Yes, please.
Is it obvious that spectral map is a continuous map, that is inverse image of a compact set is compact?
Hang on. So this is a definition.
Yeah, F inverse of O prime is compact.
Yes. So it says it's continuous.
Yeah, because your spec phi is continuous, right?
Yes. Exactly. Exactly. Oh yeah. Yes. So sorry, I should have maybe made this clearer. Yeah. So if you take an element in K node of X prime, then it's open and compact. So the pre-image is open because the map is continuous. Thank you. Yeah, the pre-image is open because the map is continuous, but the pre-image is by definition also compact. Okay. You see, this part, if I would just say continuous, I couldn't make this conclusion here. So I have to, this is kind of by brute force added onto the condition. Yeah, does this answer your question? Okay. Yeah, because we, right. Okay, so this is now how this stone duality for bounded distributive lattices reads. The spec construction becomes an anti-equivalence between bounded distributive lattices and lattice homomorphisms preserving the bound. And the other category is spectral spaces and spectral maps. And so this anti-equivalence has an inverse. I think you have seen this in the category course. And the inverse maps X to this lattice K node of X and a map F to K node of F, taking pre-images. And the ingredients this is just kind of a compact way to summarize everything I've said before. That if you write this out and breaks this down into different parts, then you will see, this is that statement, this is that statement. And so you just need to pick up the knots and then you get this statement. Okay. So then a question that people many times have, we have to look at this for commutative rings. The whole narrative is also true if you actually do this for commutative rings, except that you can't go back. So I'm not saying much more about this. So if you want to, if you start with a commutative ring, then you can also assign a spectrum and you get a spectral space, but you can't go back. So there is no, these categories are not, they simply are not anti-equivalent, the category of commutative rings and spectral spaces. Okay, just a remark for those who have seen this.
I have a question.
Yes.
We know that there is an isomorphism of categories between Boolean algebras and Boolean rings.
Yes.
So for Boolean rings, what can you say about the Zariski spectrum?
Thank you. Thank you. So this is just not just, this is a, if you restrict, so you have this, maybe I could actually, hang on, I could actually prepared something to write here. Thanks, Amit. So maybe let's make a picture, yeah. So we have this category of bounded distributive lattices. Can you see this, my handwriting?
Yes, yes.
And here's the category of spectral spaces. And there's a subcategory of Boolean algebras. Yeah. Every Boolean algebra is a bounded distributive lattice. And here is the category of Boolean spaces. And every Boolean space is spectral, as we saw in the other examples, right? If this all takes place, this is in the category of topological spaces. This sits in the category of posets, if you want. Okay, and here's this is stone duality for Boolean algebras, and here is the spec functor, and that's commutative. Yeah, does this answer your question? So this is really the classical stone duality is just a sub functor of the situation for bounded distributive lattices and spec.
Right. Okay.
These are now functors, right? This is a commutative diagram of functors. This is covariant spec, and this is how this is called. Does this have a name? I don't know. I also call it spec. Okay. This is inclusion. Yeah. Oh, yeah. This may be something I should say, that Boolean spaces form a subcategory here, because a continuous map, if you have a continuous map F from X to Y, and they are Boolean, they're automatically spectral, because F to the -1 of an open quasi-compact set in Y, take V, which is open quasi-compact, which is open and compact in Y, it's actually open and closed in Y, because this is a Hausdorff space. So now the pre-image is also open and closed. So, but in this compact space, it's then open and compact, right? So this is continuous, and they are Boolean, then it implies that F is spectral. Right, so what you see is actually just a restriction here, down.
Okay.
Okay. Good.
A very neat arrangement.
Pardon?
This is a very neat arrangement that you can also write on a piece of paper and show the slides simultaneously. We need to learn that.
Yeah, well, this is the way I'm teaching. But for students, of course, I'm writing mostly here, and I try to teach them how to read something.
Right.
Okay. Okay, any more questions? I have 2 more slides, but they have more to do.
I have a question.
Yeah.
Yeah, so can you elaborate more on the remark, like why this doesn't work with commutative rings? Like what fails there actually?
So I can maybe now refer to this book. There's a lengthy explanation about this in section section 12 of this book. What goes wrong is that you can't realize certain commutative diagrams. So, for example, I can tell you the following. So I'm giving you a subcategory that you can't send back to spec. So consider the following. The following subcategory of spectral spaces, and this has 3 objects. One object is a singleton, and the other object is also a singleton, and the next object is this space. Quickly. Okay, so I'm drawing a subcategory of spectral spaces of finite sets, of 3 finite sets, of 2 finite sets, actually. This is the same space, and this is a spectral space with 2 elements. It's just a poset actually with 2 elements, right? Okay, and now I'm drawing. I'm making a category by saying, okay, I have the identity map here, the identity map here, the identity map here. These are the homomorphisms I need, and then there are 2 other homomorphisms, and I'm sending this point to that point, to the generic point. And here I have no choice. You have to send everything to this. And this you cannot send into commutative rings. So there is no arrangement of commutative rings. So this is the identity here. There's no arrangement of commutative rings such that if you apply the spec functor of commutative rings, gives you this picture back. And so you can read this in, this is what, so you can read this in section 12. There's a section about exactly this question in this book on spectral spaces. Maybe I click on it. So that's this book that was published recently, where you can where this is elaborated on in long detail, great detail. If you send this point to the top point, then it works again. So this here is algebraically realizable, but this map is not algebraically realizable. But this is really a very different talk that we are kind of entering here, right? So this connection with commutative algebra is a very, in that context, spectral spaces play a different role, really. Okay.
Yeah. Okay. Thank you.
Other questions? Oh, it's not. Still have 5 minutes, so I can actually then say a bit more. So the last 2 slides is now towards, the first slide is 2 key ingredients of spectral spaces. Namely, if you are in a spectral space, you can attach 2 other topologies. Namely, one is what is called the inverse topology. And now I'm flipping kind of the specialization order. So I'm doing something completely crazy. I mean, this is the first time coming from maybe from a Hausdorff intuition. This looks awkward. So you're taking the open and compact sets and take the complements and you declare them all as open. And then you get a new space, which is called the inverse space. And okay, and then it will turn out that this is again a spectral space. And so this kind of on the logic side, I didn't talk about logic at all, and I won't do this in the last 5 minutes. It corresponds to taking negations, of course. And then there's and now one does something even more brutal. One takes these open compact sets and their complements, put them all together and generates a new topology, which is called the constructible topology in algebraic geometry and patch topology in domain theory or lattice theory. And then you get a space, which I write xcon, and this is a Boolean space. So is a fundamental theorem about spectral spaces says that xcon, even xcon again, is compact. And consequence of this is that xinf is spectral and has the same patch space. So this is now, this is of course too quick to be understandable now. I'm just saying what you should take from this slide is, so you have a spectral space and you can attach two other topologies to it, which again, as many times, it's maybe too much information, but of course, if you think of the spectral space as a tool to analyze the lattice, it will give you a new tool to analyze this lattice, right? This is two new tools, kind of the inverse topology and the patch topology. And but this now, I think I put that up also to connect to Priestley spaces, because now you can somehow see that there is a Boolean space popping up, this xcon, and this is the Boolean space that Nick has been talking about. And so Nick has been talking about spectral spaces in this coded form where you specify the patch space and then you specify the specialization relation of the spectral space. And this is actually the only information in order to understand the spectral space are these two components. So you need the patch space and you need the specialization relation, so which tells you which point converges to which other point. Okay, that's now on the last slide. Skip this. Okay, sorry. Now I'm actually coming to the end. This is now the last slide. So there is a tight connection to Priestley spaces. Maybe Nick will make this. He has already said this actually just 1.5 hours ago. So if we have a spectral space, now we can consider the patch space and the specialization relation. And this is now a Boolean space and a partial order. And again, I'm not saying it's up or down. You can choose, right? And then this is a Priestley space. And every Priestley space, for every Priestley space, there's a unique spectral space which produces the Priestley space in this form. And so the connection between Priestley spaces and maybe I draw the diagram that Nick had again. Nick at the end had this diagram of what was it? Lattices, bounded distributive lattices, and then there was Priestley, and there was spec, and Nick was talking about this duality. I was talking about this duality, and on this slide, yeah, it's not just a duality. These two categories are actually isomorphic. They are not only equivalent. So this is an anti-equivalence. This is an anti-equivalence, and this composes to an equivalence. But this is actually an isomorphism, and so this is even stronger than an equivalence. So you can now say, so why did you torture us? It's just the same thing. Okay, but the feature is really that you're looking, when you use this, what you do is you study this as a subcategory of top, and you study this as a subcategory of Boole times partial order. I say this informally. And the clue is that these ambient categories are very different. And this is something that one needs to realize, and kind of certain problems are easier to answer on that side, and certain problems are easier to answer on this side. And the worst thing you could do is to pick a side. So you need to learn both sides. And both sides are equally important and equally unimportant. Right? But so this is if you are on the Priestley side, you're not working with a space. So you are working with this pair. If you are on this side, you're working in the non-Hausdorff setup. So you have to pay a price, so to speak, on each side. Yes? Okay, so maybe Nick will say a bit more, or Nick will maybe correct me tomorrow, or we can talk about this in the tutorial, but maybe I stop now. I have to stop. Thank you. Thanks.
Thanks a lot.
I had a very vague question actually. Like I was just wondering, like, say if I have some order algebraic structure, then I can think about the Zariski spectrum of that. And is there exist any condition that when I can get some purely topological characterization of that Zariski spectrum of the algebraic structure?
Yes, I went very quickly over this. This was condition 3. You can condition 4. No, condition 2. Oh, I'm sorry. I messed this up. Okay. This is the answer actually. Spectral spaces are exactly the prime spectra of some ring.
Mm-hmm.
So this is the answer. This was actually a question of Kaplansky, right? What is the topological type of the spectrum of a ring? And then Hochster answered this in his dissertation, PhD dissertation. This is the answer to your question. So this question you have is a famous question, and spectral spaces is the answer.
I see. Okay. Yeah.
Right. These are exactly the spaces that pop up when you do this algebraic construction. Oh, this, yeah.
Yeah, actually it came to my mind because I was thinking about that MB algebra, and then it has some Zariski spectrum and all the things, and
Yes.
but about the topological characterization, we are thinking about like how to do that or something like that.
Yes.
That's why the question came in my mind.
This is also where the word comes from. This spectra comes from that side of the subject, that they were first studied by, well, the prime spectrum of a ring. And before Hochster, they were already studied 30 years before this was actually known, right? And people didn't look at the lattice side. They were coming to the subject with a completely different purpose. Oh, yeah, I made a mistake when I said, so this talk was about item 3 on this list.
Yeah. Mm-hmm.
Right. And so one can give other talks about other items on this list.
Thanks a lot, Marcus.
Okay.
And since you are giving only one talk, we have decided that this is the right occasion to get the group picture. So I think all the speakers are here, and all the participants who have been regularly attending and who read our email, they are here. So can I ask you to please switch on your videos? I'm going to say hide my view. Yeah. Maybe there is just one person extra. I don't know how to. So does anybody know how to change the setting so that I can see more people on the same screen?
I think this is not possible. You can only make 2 photos.
Gallery view.
Okay. In video settings, this shouldn't happen. You think so? Okay, yeah. Fine. This is video. Oh, 49 participants. Yes.
Yeah, you can have only 25 participants.
49 as well. Yeah, that's a
Okay,
good.
you got it. Yeah, you have that. So you will have 49.
Okay, so Neha Gaur, Shilpi Kumari, Vidya, and Avijit Ghosh. Can you please switch on your videos?
I am having a problem with video. I'm trying.
Okay, okay, fine.
Yeah, I'm actually joining from my phone. I'm on a PC. Just keep.
Okay. So one picture we are going to take on screen. Yeah, this is
What is actually happening?
hello, hello. The
Hello.
picture was taken already. Do you want another one? Like everybody is looking, like, should I say cheese or something? Okay, so one more. We are going to click the picture now. Yes. Thanks a lot. Now we are going to take a hybrid picture. All the offline participants will stand next to the screen. Yeah. Yeah, dais. Yeah. Then only this picture. Yeah. Click 5 on that, then they can see. 5 on the camera.
Oh, yeah. That can
So now I think you can see what's happening. We are all yeah.
I can't see anything.
No, I have switched off that video. So that's okay. Yeah. So tall people at the back. Yeah. And maybe some can sit in the front as well. No, some can sit, just duck.
I think
Yeah.
Maybe.
Yeah, you can come here. Yeah.
Don't
Don't block the view. Yeah. Yeah, this is okay. Even the online participants are there in the picture. One more. Yeah. Thanks a lot.
Thank you so much. Thank you.
Thank you.
Thank you. Thank you, everybody. So
Thank
see
you
you
to
again
all.
tomorrow in the morning. Somebody said something, please.
Bye-bye.
Bye. Bye, Marcus, Nick. You can